I would like to welcome you to our User Science Plenary session on the first day, the afternoon session. My name's Stuart Stock. I'm the APS Users Executive Committee Vice Chair. And my first duty is to invite Kamel Fiza up here to receive the plaque. He was our 2025 Gopal K. Shenoy Excellence in Beamline Science Award winner. He's been here for a long time, and it's certainly a very well-deserved honor. Thank you. Great, thanks. I should add that I've known Kamel for a long time. I think we worked together in 2001. So good things come to those who work hard and wait, I guess. My second duty today is to introduce the winner of our 2025 Rosalind Franklin Young Investigator Award. This is Lin Gao. And I invite him to come up here. He will also be our first speaker, so. Great, yeah, thank you. And he will be talking about additive machining.
Okay, I'll get started. Thank you so much for the introduction, and also thank you all for your coming to this presentation. My name is Lin Gao, currently a postdoc appointee from the Nuclear Science and Engineering Division of Argonne National Laboratory. So today I'm going to present some of my research on additive manufacturing. So this work will include 4 sections, and it will have 3 research examples about how we leverage the advanced operando synchrotron X-ray characterization to study the multiple stability involved in the metal additive manufacturing process, and also how to leverage the new findings to achieve the microstructure control in the practical application. So first of all, I would like to briefly introduce additive manufacturing. So additive manufacturing, also known as 3D printing, is a group of layer-by-layer manufacturing technologies. So it typically started with a 3D model, so you can use a computer to design a 3D model of a specific product. Then the computational program will slice this 3D object into thousands of layers. Then the additive manufacturing machine or the 3D printer will deposit the materials layer by layer. So eventually you can directly print a 3D object with designed geometry. So because of this novel manufacturing strategy, so additive manufacturing have gained great attention in many sectors, and it have many advantages against the traditional manufacturing method. For example, it is a near-net shaping tool, so it is available to contribute to the sustainable manufacturing requirement for our current society, and also it can help to rapidly customize specific parts or reduce the cost in customizing specific parts. So that can greatly benefit in some critical industries that are facing limited supply chain challenges. So the fusion-based additive manufacturing is a type of technique, especially it's particularly used for fabricate metallic components. And based on the working mechanism, so the fusion-based additive manufacturing can have powder bed fusion, laser directed energy deposition, and etc. So directly energy deposition is an additive manufacturing process that utilizes a highly concentrated energy source so that can directly melt the metallic feedstock, which is constantly feed from the deposition head, and directly deposits materials on the substrate. And because of this, because this technique have pretty faster deposition rate compared with other additive manufacturing techniques, so it's especially benefit in printing large scale components. And also based on the type of the feedstock used, so the DED can have powder balloon DED and wire feed DED. So in general, the wire have many advantages against the powders, although these two techniques have their own specific applications. So in general, the wire have relatively low cost and better quality control and the improved operation safety compared with the metallic powders. And also, the wire works better in specific environment. For example, for the in-space manufacturing. So it still requires a lot of effort to further study and develop this wire-based additive manufacturing technique. So the first generation of the wire-based directed energy deposition have been developed with a lateral configuration, about as sketched over there. So for the first generation of the DED system, so it have laser deposition head irradiate the laser perpendicular to the substrate, and it have a wire feeder constantly feed the wire from one side of the deposition head. But this type of design have a very big issue, is that it shows a stronger directional dependence. So which means that if you print the sample along different directions, you may get quite different printing quality and get different microstructures. So to solve this problem, and recently a coaxial wire laser deposition head has been developed. So for this deposition head, so it have a wire feed through from the geometry center of the deposition head and have multiple lasers around it. So it can provide a very uniform energy distribution and mitigate the directional dependence. But because this is a new design for the printing for the deposition head, so there still have many printing behavior unclear and still have a lot of underlying mechanisms needed to be further studied. So the wire-based directed energy deposition, like other fusion-based additive manufacturing techniques, it involves a lot of critical but complicated physical events compared to the traditional manufacturing method. For example, because it utilizes a highly concentrated energy source, so it involves a rapid energy transfer between the energy source to the matter, and also because of the intensive heating, a mole pool will generate at the deposition region, and the mole pool will subject to highly dynamic melt flow and the steep temperature gradient inside. And the mole pool will move together with the heating source and very rapidly, so the rapid solidification will take place at the end of the Mushi zone and accompanied with a lot of complicated solidification behavior. For example, the heterogeneous nucleation, the epitaxial grain growth, and etc. And the solidification microstructure strongly depends on the thermal conditions inside the mole pool. For example, the temperature gradient G and the solidification rate will have a great impact on the morphology and the size of the solidification microstructures. And because the mole pool typically have a very complicated thermal conditions, so typically the additive manufacturing will generate the materials with very complicated and hierarchical microstructures, like from the micron scale to nanoscale. So the current objective of additive manufacturing is to achieve better microstructure control, because that is very essential for the practical application of the additive manufacturing product in specific industries applications. And the mole pool behavior is actually the key for us to understand the relationship between processing and microstructures, because the printing parameters will directly influence the mole pool behaviors, and also the thermal conditions inside the mole pool will control the microstructure generation during the printing process. So over the past decades, so additive manufacturing community have been pursuing for a very stable mole pool because people believe stable multiple can help to mitigate the defect generation in the printing process. So this is true. But here the video shows a wirelessly directed angular position of a 316L stainless steel. So you can see that although it is under the optimized printing condition, so we can still see a natural and intrinsic multiple instability during the printing process. It is because the additive manufacturing process is actually influenced by many highly dynamic phenomena and the stochastic events during the printing process. So it actually reminds us, instead of pursuing perfectly stable multiple, can we actually leverage and amplify this type of multiple instability to achieve the maximum control? But before answering this question, so how can we study the multiple behavior? So a very general and effective tool is about high-speed optical imaging. And the setup is very straightforward. You only need a high-speed camera set up in front of the 3D printer and focus at the printing region. And this type of technique can monitor the entire printing process, from the very beginning of the printing to the very end of the printing practices. And also it can compatible with other accessories, for example, the near-infrared lens or the digital imaging correlation to monitoring the temperature evolution and some other microstructure evolution during the printing process. But there are two limitations for this technique to get a very in-depth understanding about the multiple behavior. So the first one is about that this technique is only a surface technique. So you are not be able to get any information from the multiple interior. And also it is not capable of detecting the structure evolution during the manufacturing process. Because for the rapid certification process, the material may subject to the solid state phase transformation, but this technique is not be able to provide this type of information. So these two limitations actually motivates us to pursue more advanced techniques to characterize the printing process in situ. The third generation synchrotron X-ray source actually provide a very powerful tool for us to study the additive manufacturing processing. So here is the sketch shows the synchrotron facility. So like APAs, it typically have a very large storage ring, like for the diameter of hundreds of meters. And they have multiple beamlines set up around this ring. And each beamline can utilize part of the high energy electrons to produce the X-ray for different characterization techniques and for different materials. And in 2017, the Advanced Photon Source at Argonne National Laboratory pioneered the first application of operator synchrotron X-ray characterization in metal additive manufacturing. So the 32 beamline and the team established the laser chamber at the beamline, so it can mimic the laser pulse fusion process. It is another mainstream additive manufacturing technique. So you can fire a laser, scan over a piece of metal, and the high-speed X-ray can monitor the entire printing process and offers a transparent view about the multiple evolution during the printing process and help us to understand a lot of highly dynamic physics involved in the printing process. And also with the further development of this operator synchrotron characterization, and it has been applied to more and more fundamental study and also applicable for other metal additive manufacturing techniques. And our team conducted the first operator synchrotron X-ray characterization for wireless DED. So we modified a wireless DED system in our lab and brought it to APS for the operator synchrotron X-ray characterization. And especially, this sketch shows the detailed experiment setup in our characterization, and it actually have a more unique design for the collection strategy. It actually offers us some new insight for the operator synchrotron characterization on the additive manufacturing techniques, and I will elaborate this in the following slides. So before this, I would like to briefly introduce what the existing effort on or the previous work on the synchrotron X-ray characterization. Actually, most of this type of characterization, including the first experiment developed at APS. So we adopted the Lagrangian reference frame. So which means that the sample or the substrate is always fixed with respect to the incident X-ray, and the relative movement was carried out by the energy source, like shown by this very nice video. And also, this type of strategy is also applied for the in situ X-ray diffraction at 180 in beamline at the APAs. So the X-ray was probed at a very tiny window and with the X-ray scanning over this piece of metal, and then continuously collect the data during the printing process. So this strategy is very effective because for each individual measurement, you can cover the entire printing process of this single track. But one issue for this strategy is that because the additive manufacturing is a highly dynamic process, like it's subject to a very rapid cooling process. But with this characterization, so for each individual moment during the rapid certification process, you only got a very short exposure time, like in milliseconds. So actually this exposure time is too short to get a very high quality data for quantitative analysis. So to address this issue, so we have a more special design for the data collection strategy. So we adopted a Eulerian reference frame, so which means that the deposition head is always fixed to the incident X-ray. So the relative movement was carried out by the substrate. So actually, it enables us to probe the X-ray, especially for the diffraction mode. We can probe the X-ray at a specific location for a relatively long time, like in the second scale. So here the X-ray imaging shows the entire printing process. So we can see that with this collection strategy, we can actually have we can keep the multiple at the same location of the field of view for a relatively long time during the stable printing process. And also, we can integrate this with the diffraction mode to get further details about the microstructure evolution during the printing process. So here is the diffraction mode. So instead of the full field X-ray imaging, so we focus the X-ray to a very tiny size and continuously collect the data during the printing process of a single track. So here the video shows the entire data set collected during a measurement. And for each video, it actually consists of thousands of individual diffraction patterns that was continuously collected during the measurement. And each diffraction pattern is like a fingerprint of the multiple or the materials at a specific location and at a specific moment. And for the diffraction pattern, we can convert it to line profile analysis, line profiles to do further analysis. And because we have a batch of diffraction profiles, so we can compile them together as a function of time. So we can get a waterfall diffraction intensity map. And actually it has 3 different areas corresponding to 3 representative moments if we convert it into the real space, like reflected by the X-ray imaging. So at the very bottom region, because it is corresponding to the beginning of the printing, so there are no any signals from the sample, and the second region is corresponding to the stable printing process. So it actually includes thousands of diffraction patterns. So we can sum up all of these patterns to get a very good data quality for quantitative analysis. And the very top region is corresponding to the end of the printing. So the X-ray was probed at the end of the printing track. So we can also get some information about the rapid cooling. And also, we can probe the X-ray to another location with respect to the multiple, so that, and repeat the printing. Then for the second data set, we can actually collect the data for another specific location of the multiple. So then, if we repeat it multiple times, so we can get a diffraction mapping to resolve the 3D, maybe the 2D structure of the multiple, like with pretty high temporal and spatial resolution. And in addition to the synchrotron X-ray characterization, we also conducted the high-fidelity multi-physics simulation to simulate the printing process. So we can integrate a lot of physical models into the modeling, and also like directly adopt the exact printing configuration of our printer into the modeling. So it can get a lot of valuable information that is very difficult to be directly measured by any experiment. So we have pretty good validation for the modeling, and this is a video shows the printing process of the wire-laser LED. So now we have a very powerful and effective tool to study the multiple behavior. Let's go back to the previous question, whether we can amplify and leverage the multiple instability to control the microstructures. And our answer is yes, we can. So the first topic is about the thermal conditions and the texture control. So we know a current challenge in metal additive manufacturing is about the coarse microstructures and the strong crystallographic textures. So because the steep temperature gradient inside the mold pool, it will promote the grain growth during the rapid certification process of wire laser DED. And so all these grains are preferably growth along a specific direction, therefore resulting in a very strong crystallographic texture of the printed sample. And because of the crystallographic texture, the additive manufacturing product will typically show a very strong mechanical anisotropy. So which means that if you load the sample along different directions, you may get quite different mechanical properties. So it definitely influences the application and the challenge of the qualification of the additive manufacturing products. So in order to solve this problem, so because we know that the stable thermal conditions inside the mold pool contribute to the grain growth and the texture evolution. So how about if we constantly alter the thermal conditions inside the mold pool? Like if we can generate a more turbulent thermal conditions inside the mold pool, whether it can help to control the crystallographic texture generation during the certification process. So for this, we designed a very special printing strategy that instead of the normal printing process, so we constantly alter the printing direction by 90 degrees. It's like cause a wobbling of the mold pool, and it is expected to induce a certain degree of multiple instabilities. And then we conducted the high-speed optical imaging to study the printing process under these two different strategies. And from this video, we can clearly see that compared with the traditional manufacturing strategy, the wiggle deposition process is able to constantly wobble the mold pool and cause a more dynamic thermal conditions on the mold pool surface and cause a specific mold pool instability. So then, based on this, we conducted the multi-phase simulation, and from the simulation, we can directly extract the thermal conditions inside the mold pool. And very interesting that, so as shown by this plot, so the wiggle deposition process shows a very fluctuating thermal conditions along the transverse direction. It's a direction perpendicular to the scanning direction, and this type of thermal conditions is expected to influence the certification behavior. So from this simulation, we confirmed that this type of multiple instability we observed from the optical imaging is able to influence the thermal conditions inside the mold pool. And also we conducted the open-ended synchrotron X-ray characterization by probing the X-ray at the mushy zone of the mold pool. So that is a region consists of both the liquid phase and the solid phase. And by analyzing the stability of the scattering intensity of the scattering data, we can actually analyze the stability of the mushy zone. And for the wiggle deposition process, we can see the more obvious fluctuation of the intensity, so which means that the mushy zone will move back and forth. That is consistent with our simulation data. So from this whole experiment and the study, it tells us this wiggle deposition strategy is able to influence or alter the thermal conditions within the mold pool and influence the certification behavior. So now we know it works. Then we applied these two printing strategies to the practical application of a bulk sample. And both of the samples shows very similar grain morphology and grain size. But these two samples shows quite different crystallographic texture as represented by the different colors on the EBSD map. And in addition to this, we conducted a more detailed microstructure characterization, like the element segregation, the macro hardness, and the printing defects. But all these features are the same in both samples. So it tells us, and also we conducted the mechanical property test for both samples. And very interesting that in these two samples, we observed a distinct mechanical anisotropy. And we conducted the crystal plasticity simulation and confirmed that the different texture in these two samples are responsible for the distinct mechanical anisotropy of the additive manufacturing product. So from this work, we have a very important outcome that during the printing process, we can induce a dynamic laser distribution to induce a certain degree of the multiple instability. Thereby, we can use it to control the solidification process, the texture generation, and the mechanical properties of the final product. And also, this strategy has many advantages against some other existing efforts or methods. For example, there is no need for external accessories, and there is no need to sacrifice the optimized printing conditions. And also, you can even use this strategy to program a layer-wise texture precisely. For example, if you need to print a very large-scale sample and you have thousands of layers, and actually you can freely select the different printing strategy at each layer to satisfy a specific requirement of this large-scale components printing. So the second topic is about the feedstock and the grain control. Because we know, like, during the printing process, a good balance between the power input and the feeding rate is required. And this is described by the volumetric energy density, so which is a function of the energy of the power input and the feeding rate. But if the power input is too high or the feeding rate is too low, actually you may cause a dripping phenomenon because the wire is overheated and the boiling on the wire tip can discontinue the printing process. But if the feeding rate is too high and the power input is too low, you may get a stubbing effect, so which means that a large portion of the wire cannot be fully melted. So it will cause a lot of printing defects like cracking. So only within a good balance of these two parameters, you can get a relatively good printing. But even within this optimized processing window, so there's still some space for you to finely tune the printing parameters. And it is also still unclear whether it will influence the melting behavior of the wire feedstock inside the mold pool, and whether we can leverage this to control the MAC structures. So to study this, we designed a specific printing condition so that we intentionally reduce the volumetric energy density, but it can still, as much as we can, but we can still maintain a relatively stable mold pool. And we conducted the operator signature characterization at APAs for this specific printing condition. So here is the X-ray imaging and the diffraction mapping for the mold pool structure under this specific printing condition. So for region A to region C, so we can see that there are still many sharp diffraction peaks observed corresponding to these regions. So that means that under this specific printing condition, actually the solid wire cannot be fully melted as it is inserted into the mold pool, but it can arrive at the bottom region of the mold pool. And for region D and region E, so the diffraction peaks disappear. So that's corresponding to the fully liquid region. So that means that the wire is fully melted over there. And for region H, so the diffraction peaks shows up again. So that means that the solidification starts since here. So it's corresponding to the solidification front. And as I mentioned before, because for this region, it is supposed to be a fully liquid region because the diffraction peaks disappear. But actually, these patterns are summarized by thousands of individual diffraction patterns collected during the measurement continuously. So if we check the diffraction patterns frame by frame, actually, we can occasionally see some diffraction spots corresponding to some solid particles. So that means that actually in this region, it is not fully melted or not fully liquid. So we did a phase index and did a comprehensive statistical analysis about the distribution of this diffraction signals corresponding to this fully liquid regions. And eventually we concluded that these particles are the type of refractory particles in these materials, and they are actually released from the wire tip. And it concentrates at the bottom region of the mold pool, and it can be transported to the solidification front. Because we know in the mold pool, if we have the presence of some solid particles, it will influence the solidification behavior. For example, it can induce the heterogeneous nucleation of the grains. And in the cross-section of the printed track, we do observed some refined grains at this specific location. And we did the SEM characterization, confirmed that and compared especially the size, morphology, and the distribution of the refractory particles among these regions. And then we found that the unmelted particles in the mole pool is responsible for this type of microstructural heterogeneity. So in addition to this, we conducted the multi-phase simulation to analyze the other factors that could contribute to this microstructural heterogeneity, and especially the thermal conditions. And in analysis, we confirmed that this thermal conditions is not responsible for the grain refinement we observed before. So that means that the refractory particles are the major reason for that microstructure. So actually, this work offers us a very important insight that even under the optimized processing window of additive manufacturing, actually we can still have many space to finely tune the printing parameters to control the melting behavior of the wire feedstock. And it can also be used to control the local microstructures. So the third topic is about the local dynamics and solidification. So we know in metallurgy or even in metal additive manufacturing, the melt flow can greatly influence the solidification behavior. For example, influence the grain morphology and the element segregation. And in last section, we discussed that even within the optimized processing window, we have some space to finely tune the printing parameters to control the melting behavior for the wire while still keeping a relatively stable printing. So it reminds us whether we can control the melting behavior for the wire inside the mole pool to control the flow pattern of the inside the mole pool, because we know the mole pool typically have very complicated melt flow patterns, and whether we can control this to further control the microstructures. And for this research, we found a very unique printing condition that can trigger abnormal grain refinement in the printed track as shown here. And this is called abnormal because of two reasons. The first reason is that it can greatly reduce the grain size from millimeter scale to micron scale, and this is much effective than any efforts to manipulating the solidification process. And the second reason is that this solidification process is not be able to be explained by any existing solidification theory or solidification mechanisms. So it motivates us to get a further understanding about this printing process. So in this investigation, we did a little bit modification of our synchrotron characterization so that enable us to do an operando total scattering analysis and the pair distribution function analysis for the liquid metal. That is the mole pool under the additive manufacturing condition. And with this technique, so we conducted the pair distribution function analysis, revealed some that the mole pool have a lot of atomic clusters, so that enable us to reveal the atomic scale microstructures of the liquid mole pool under the additive manufacturing, under the real metal additive manufacturing condition. So this is for the first time. So we get this type of information from the operando synchrotron characterization. And beyond this, we conduct a more comprehensive operando synchrotron X-ray characterization to study the atomic structure of the mole pool, and especially how these atomic clusters evolve during the rapid solidification process, and how this type of clusters can assist the rapid solidification process, especially associated with the abnormal grain refinement we observed in our previous experiment. And because of the time limitation, I'm not be able to cover all the details of this work, but this work is to be submitted soon. And so I would like to briefly summarize the presentation today. So in this presentation, we just discussed the mole pool instability, and also from three aspects. We discussed how to leverage the new understandings to achieve microstructure control, and also with the rapid development of additive manufacturing. So a very urgent objective is that how to achieve more flexible microstructure control in the printing process. So this objective actually motivates us to pursue a more in-depth understanding about the printing mechanisms. And the operando synchrotron X-ray characterization is a very powerful and effective tool, and it can link with the pulse characterization and the multi-phase simulation. Actually, it offers a new avenue for us to study the printing mechanisms. And the new findings actually can help us design the more innovative printing strategies to achieve microstructure control in practical application. So finally, I would like to appreciate my PhD supervisor, Professor Tao Sun, because all of this work I mentioned today was supervised by him and conducted during my PhD. And also I appreciate all my co-workers from the University of Virginia and from the Northwestern University for their support. And also I appreciate the synchrotron beam scientists at the APS for their very professional support on the synchrotron characterization and guided me for the data analysis. And also I would like to appreciate the kind support from my current colleagues and the supervisor at the Nuclear Science and Engineering Division of Argonne National Laboratory. Thank you.
Thank you. Yeah, very impressive in situ characterization. So you capture the diffraction signal at different locations in the melt pool.
Right.
How did you incorporate that information in the simulation?
Yeah, for simulation, actually we have the X-ray imaging to validate our simulation. But for the simulation, the main goal, the primary information we got from the simulation is thermal conditions, because that is very difficult to be extracted from the synchrotron characterization.
So you haven't used the diffraction and the corresponding grain orientation or phase information in the simulation yet?
Yeah, currently we didn't do much like this kind of things for the synchrotron characterization, because we know, like for our modeling, because we don't have a phase field model, so it's not be able to get more information from simulation. Like
you have a very valuable information that has not been used. Probably we can discuss. Yes. Thank you.
Thank you.
Mm-hmm.
So on the picture you have there, I just want to make sure, when you have all of these microstructures actually in the melt pool, so there's a melt with microcrystallites floating in the melt? Is that what you're seeing with the diffraction?
Oh, you mean for this plot?
Yeah.
Yeah, this plot is actually corresponding to this region outlined over there. So actually is inside the printed, it belongs to the printed track. Actually, so the dashed line marks the interface between the substrate and the deposited materials. And you can see that we have a specific region with very refined grains, but all the outer regions are corresponding to the coarse column grains. Like, yeah, sorry, I don't have an image of there.
So that's a dynamic structure. It's not stable, but it's just moving as the melt pool moves?
It is within the melt pool, yeah.
Thank you very much.
Yeah, thank you.
Yeah, that's a really interesting work for the liquid atomic structure in the liquid melt pool.
Yep.
So what's the temperature of the liquid? It's a supercooled liquid, it's at a melting temperature, above melting temperature?
Yeah, we actually, in our analysis, we did both. So this is the reason why we can investigate the evolution of these atomic clusters during the rapid certification process. And for the normal certification process and the abnormal grain refinement, for these two processes, we get quite different evolution path of the atomic clusters. So that tell us that the atomic clusters really matters for the different certification behavior. So part of we got information from both the equilibrium or the high temperature liquid and the undercooled liquid.
Okay, so you see different atomic structure at a high temperature liquid and the low temperature liquid.
Yeah, because especially based on the configuration of these atomic classes, because we have like for these atomic classes, they may have different structures. For example, the exohedral structure and the FCC-like structure, and etc.
Do you have any estimation about the the undercooling you get, how many degree of the undercooling?
Sorry, could you say it again?
The undercooling you have in the liquid, you can reach.
No, we don't have much information about this, but we think a more advanced modeling could be very helpful for us to, yeah.
So I had a question, and that was, when am I going to be able to buy something made out of this? You know, this is just, of course, speculation, but how long until it comes out into this type of approach, comes out, you know, with tailored texture in something I buy?
You mean how soon it can be utilized in the
Speculate.
Okay.
Yeah.
Yeah, I think it depends on whether we can get funding for this.
Okay, let's assume in the best case scenario you've got funding.
Yeah, but this is a very good concept that tell us like we can like, actually it's not only, so actually one potential of this work is that actually, because in our work we only adjust the mobile wobbling with a specific phase. Like we can further adjust the angle, how it wobbles and the path, so it can get a further freedom to tailor the crystallographic texture, like with a specific orientation. If we want 112 or 113, right, we can, that is our hope. Yeah, but this is my PhD's work. I really hope that the new students can pick up this and do further research on this. Yeah.
Let's thank our speaker.
Thank you.
So our next speaker is from the CNM side of things. It's Wei Biao talking about things I don't know very much about. I remember encountering them a long time ago, but I'm hoping to learn a lot.
Thanks, Stuart. It's a great pleasure to visit Argonne again. So my first visit back to 2022. Yeah, my name is Wei Bao from Rensselaer Polytech Institute. We are located at Albany, New York, the capital of New York State. So today I'm going to talk about our work on new room temperature playground for Bose-Einstein condensate using halide perovskite. Okay. So talking about the BEC in 2025 is a special time because back to 100 years ago, a century years ago, Werner Heisenberg took a special trip in Helgoland. Now this become a special place everyone wants to visit to see the birth of quantum mechanics. And in the same time, back to the 1925, Bose and Einstein also proposed the theoretical framework about the Bose-Einstein condensate. So let's zoom in a little bit. For me, myself, I graduated in the 2015 from UC Berkeley doing near-field optics. And at that time, everyone in the field know that our pioneering in the field, everybody got the Nobel Prize. Seems like the end of the near-field optics because all the theoretical framework has been already done. So at that time, I'm struggling to looking for new topics as a postdoc. So luckily, one of the smart people that Dr. Xiaoze Liu and I joined Professor Xiang Zhang's group in the same time at UC Berkeley. So we started work in the field called strong light matter coupling and the room temperature Bose-Einstein condensate. So from 2015 to now is almost 10 years. So I think talking about this has a special meaning to me. It's a 10-year memory. So a little bit background. As we all know, fundamental particle can be classified as a fermion or boson. For example, our typical electron or helium-3, those are fermion, where they have a Pauli exclusion principle. Essentially, you cannot put the same particle in the same quantum state without changing parameters. while the other particles are classified as a boson. Typical boson are photon, phonon, and exciton. Those don't need to restrict by the Pauli exclusion principle. You can put arbitrary number in the quantum states. So what's the consequence? The consequence is if you have two different systems, you try to lower down the temperature. For boson system, you will become massively occupy the ground state to minimize the system's energy. Such a massively occupied ground state, take the ideal gases, for example. At the very beginning, when the temperature is high, your high temperature, high energy part has a noticeable occupancy, and the low temperature one has a higher occupancy. As you're going down the temperature further lower, your low temperature part, the low energy part become to more and more occupied until you reach a critical temperature we call the TC condensate. In Albert Einstein's original word, that means he said one part of the ideal gas become massively occupied, condensate, and saturated as a one part of a quantum particle, and the rest remain as a saturated gas, follow the Bose-Einstein condensate. So this is quite interesting. Although theoretical proposed back to 100 years ago, the experimental demonstration in the ultra-cold atom has only been realized 70 years later after the theoretical proposal. So essentially the experiment was done by cold atom, ultra-high vacuum chamber with ruby atom with a magnetic trap, laser interference trapping, and eventually the consequence of this, once you go down to 170 nanokelvin, the ruby atom become massively occupied in the energy minimum state. So essentially K equal to 0, Kx, Ky equal to 0. So that is the energy minimum state. And then they become coherently behave as a one macroscopic sizable quantum object. So you can physically observe those. So the only downside is the condensation temperature is happen at 170 nanokelvin. It's about 9 order magnitude lower than the room temperature, which is one of the coldest place you can find. So due to this pioneering work, 2 Nobel Prizes given, one on the laser cooling, the other one is the real BEC work. So if you trust my copy-paste capability, so you will realize the critical transition temperature is actually, in the 3D case, can be written down as this formula. So there's a bunch of constants, and the only thing that is tunable is the effective mass of the boson system, and then the density of the boson system. So in other words, if we can find another boson system compared with ruby cold atom, that you can have the boson system has a higher density and a lower effective mass. So that means our Bose-Einstein condensate transition temperature will go up, even up to room temperature. So our goal is to find another boson system that has a higher density, easily achievable, and a lighter weight, and then lead to a higher transition temperature. We don't have to bother to go down 9 order magnitude lower than room temperature. So smart people quickly realize for a system like if you hybridize light and the semiconductor together, you will form a new quasi-particle called a cavity exciton polariton. They can merit both higher density of the particle and the lighter effective mass in the system. So how that works? So essentially, if you start with a good semiconductor, typically MB grow quantum well, those high quality quantum well has no defect, has high quantum yield, and what's lead to is once you pump it, they generate a new quasi-particle called exciton. So essentially one electron in the conduction band, one hole in the valence band bound together by the Coulombic interactions. And if you bring this excitonic material embedded into an optical cavity, what's going on is the exciton will start to recombine and give out photon. And the photon trapped by this really good optical cavity, and so they have no way to go, they have to be reabsorbed by the semiconductor. And so the exciton emit to photon, photon reabsorbed by the exciton. So only after a couple of this coupling, and then they can leak out finally outside the cavity. So in other words, that means if you, with the coupling rate much larger than the non-radiative decay rate of exciton, essentially the exciton gave phonon instead of photon, and then the photon without couple directly leak out to the cavity. So if your coupling rate is much larger than those two rates, what you detect outside of the cavity is always the hybridized state. We call this a polaritonic state. So essentially, if you try to appear to be more knowledgeable in front of people, you say, oh, this is by Dirac notation, this is a photon, exciton, linear combination together, and originally EK relationship from the flat exciton and the parabolic photon now become upper polariton and the lower polariton. And then by the cold atom definition, this is the Rabi splitting in between. And if you see the effective mass here, and following the effective mass formula, and you will see this effective mass is almost 8 order, 9 order magnitude lower than the cold atom. So essentially, because this is a semiconductor system, you can easily pump with lasers to generate more exciton, and then it essentially lead to more polariton. So the exciton part provide interaction with essentially exciton-exciton interaction and the nonlinearity so that you can have more density of the particle, while the photon part provides small mass. So those hybridization do bring benefits from the both sides. Just like, if you get married, you want to have kids, you want the kids to marriage both the advantages from the father and the mother. We don't always achieve that. But if sometime we achieve this, that's lead to some good things. So if you, because this is argon, if you listen to our previous directors, Peter Little-Wu's talk, he probably tell you in a more intuitive way. So essentially, you have exciton, you have photon, you couple them together. This is another classical picture about this coupling about the cavity exciton polariton. So indeed, with this exciting concept, the first convincing exciton polariton condensate happened in this Nature paper back to 2006. So essentially, they have a cat-telluride quantum well in where they keep the system at a really constant temperature and increasing the particle density by pumping the system harder and harder. So as they increase the system's particle density, you can see indeed they undergo a Bose-Einstein condensate similar to the ruby atom, and then the Kx, Ky equal to 0, the energy minimum point start to massively occupy. And what's more exciting is you see a noticeable blue shift. That means the interparticle are interactive as well. It's not non-interactive. There's a little bit interactive because those are critical for later on to study the superfluidity and many other interesting physics. So although the first experiment demonstrated that the cat-telluride can see alleviate temperature 19 Kelvin, it's still liquid helium temperature. It's not quite room temperature. So people, after this initial success, start to searching for room temperature exciton polariton BEC. The main problem typically associated with that is you have many of these inorganic quantum well systems where the exciton don't sustain the room temperature thermal fluctuation. Our room temperature has a thermal fluctuation about 26 MeV, but the exciton binding energy for most of the semiconductor is below that value. For some rare case like zinc oxide or gallium nitride, we suffer from the inhomogeneity growth. If you try to use the experiment to mimic this cold atom experiment, you realize your artificial atom is different in different place. So that's not ideal. And of course, when I started the field, people also work on the two-dimensional TMDC, where they have high binding energy, hundreds of milli-electron volts, 10 times the room temperature thermal fluctuation. But those are low quantum yield. You pump the system, you pump it 10,000 photons, they give it only like 1 photon out. So those really suffers. No one can see a Bose-Einstein condensate easily. So while I struggle, one of my friends at Professor Peidong Yang's group at UC Berkeley showed me that his group working on some excitonic material called halide perovskite. And we got great inspirations. So essentially, although it's organic, inorganic, hybridized material, but most of the halide perovskite can be written down just as STO3, those traditional oxide halide, traditional oxide perovskite. You essentially have octahedral. Those are the inorganic part, and then you have the corner sometimes mixing with organic part. But luckily, all the exciton part is actually associated with the octahedral inorganic part, which means they are Wiener mode type of exciton, which can very similar with gallium arsenide, gallium nitride, and who are sizable binding energy and high quantum yield. So indeed, if you have the cesium-lead chloride, bromide, iodide group as a material, you can see they have very bright photoluminescence, the tunable photoluminescence, and then the peak are very narrow, suggesting the high quantum yield. And some of my friends always ask me, you have lead, this is toxic, and then you call this a perovskite mainly to hide you contain lead. But if you consider our drinking water, they have a standard that lead you need 5 ppb. Arsenide, typically physicists work with gallium arsenide, is 10 ppb. It's equally toxic as arsenide. So we wouldn't worry too much as long as we run the environmental regulation. So there's a stable exciton form at room temperature with cesium-based halide perovskite. For example, for cesium-lead chloride, people measure it's about 70 or 60 MeV. And if you really lower down the temperature, you can even see the Rydberg state, essentially higher excited state of this exciton. So those are really rare in a solid state system. You only see this with high quality, MBE system traditionally. But with here a solution process or CVD process material, you can see this really 1s, 2s, really nice. And then the binding energy in our measurement shows is a cesium-lead bromide has 36 MeV and cesium-lead chloride has 64 MeV. So those are really stable against room temperature thermal fluctuation. So one of the issue before my independence back to the 2019 is that although there's many papers try to reproduce or do it better compared with gallium arsenide or telluride, many of the work has been done with a CVD grown sample, which have very small size. You can use a laser to pump it and generate one spot of the BEC, at room temperature, but you cannot do much compared with the cold atom, community, or even compare with gallium arsenide telluride to do some meaningful physics study. And so once you have the sample, you can only exfoliate it with the famous Nobel Prize winning method, the Scotch tape. Right? It essentially transfer this into the substrate. So those are not ideal. So I started my independency back to University of Nebraska in 2019, and to many of the people even don't, in my friends who originated California, even don't know in the map where is Nebraska, which is kind of good, so and bad. So the good thing is I have time to think about about the research in more details, and also my postdoc don't have way to entertain. So they got stuck in the lab to work 24 hours, 7 days. On the other hand, we do have entertainment. You can go to flat land or flat water, see a lot of the cow, right? Especially we currently have a trade war with China, so the Nebraska cow probably have no way to sell. So at that time, we do spend a lot of time with my group, do a group entertaining to see the cow. And then the other entertaining place we have is visit Warren Buffett's house, right? Well, as we recently heard from the news that Warren Buffett complained, right, and then going to step down to the Berkshire Hathaway CEO, right? I do learn how to play with stock in Nebraska because it's nothing to bother. But on the other hand, so I also in the big house of Nebraska think about what else can be done. So essentially, revisit the motivation. We have the condensation at 1 microkelvin, right? The ruby atom. We have the condensation as a gallium arsenide telluride system about 10 Kelvin. But for room temperature, there's nothing. You have a 1-point spot measurement. You can barely claim this is a Bose-Einstein condensate, but there's nothing, physics measurement can be comparable with cold atom, or even compare, try to study any physics with it. So our goal is essentially to reproduce something with our system with the BEC as good as a cold atom. So there's many interesting physics, a problem that even gallium arsenide can study, but the room temperature system, none of them can study. For example, we can study in gallium arsenide superfluidity with a liquid helium temperature. We can study the spin model. One can also study the topological physics, which appear to be hard in the cold atom, but none of them is possible. So in one of the MRS meeting, I met with one of my friends, Professor Stephen Cohen, who used to do his PhD work with Stephen Forrest at Princeton, and then later on with Michigan. So in their early work with the physical review letters, there has an interesting thing that he demonstrated essentially with a pre-made cavity mirror, and then use gold as a spacer, eventually use a metal-metal fusing bond to bond these two mirrors together, and eventually form this organic material into the channel, and eventually make a single crystal organic inside a pre-patterned nano channel. But what happened is in this growth, they show the polarity mode variation, even though it's single crystal, they are like 50 MeV. So essentially it's 2 times the room temperature thermal fluctuation, which is not good. So they only publish in the physical review letters. But I try to extract some of this idea, right? Like the Nebraska tradition in the Warren Buffett case, you can have a McDonald's with Buffett and pay $20 million and to extract some of his wisdom. So I do the same thing, but without paying this much money from Stephen Cohen. And eventually the conclusion out of this meeting, I realized he didn't make the mirror careful enough, and then the bonding was carried out by a chip level fabrication. So in order to improve it, we decide to use a different method. So essentially slightly modify this. We start with the 6-inch wafers and then make it ultra clean and then fabricate it with just the detection of the gravity wave to make the mirror really as flat as the wafer. And then with high quality gold pillar pattern the entire 6-inch wafer with a variation about 1%. And then afterwards we do wafer scale bonding, and eventually cutting this into later on small chip. So the wafer scale, you have 1% variation, but in the center of the chip, you have 0.5, 0.2% of the variation. So they make as flat as a cavity, as flat as an MBE sample. And then use that template, we grow the material in this very high homogeneous template. And then this is the cesium lead bromide, cesium lead, amide lead chloride, PEPI, the organic, inorganic process. They all has the sizable exciton, and then you can see the sample is really big and homogeneous. So here is the cavity we made. This is without DBR mirror. This is with the DBR mirror. Optically, they are really homogeneous. And then we show the growth also. The science behind it, if you don't have confinement, you have a lot of nucleation happen in the liquid. But with the confinement, you have limited nucleation. They tend to grow bigger crystal, single crystal, instead of small crystal. So if you characterize the film, those are with UV lamp, you see the homogeneous photoluminescence, and then with the size of hundreds of micron, sub-millimeter size, you can do a spatial light patterns and all kinds of patterning with it. So the ultra-homogeneous potential landscape we can also characterize with AFM by opening the cavity, and we see this sub-lattice level of height variation. And if you also do a polarity mode of mapping, in our case, we see a peak-to-peak variation about plus minus 3 MeV. So essentially, if you convert it into RMS roughness, that means we have a RMS roughness of 1 MeV. So compared with room temperature, now we have almost 5% of the room temperature thermal fluctuation. Our sample compared with room temperature is ultra flat. So that means if you create artificial atom, the BEC condensate, it becomes everywhere the same atom instead of different atom. So the material indeed can run into condensation with strong exciton interaction. You see the blue shift, and this is showing after the condensation the clearly G1 coherence. So essentially you have a macroscopic quantum object that everywhere share the same phase. So the method later on further developed by our colleague in Poland. So in this nature material, they use PDMS as a template, even can pattern, various shape of the material. So the interesting physics one can study, the first thing coming to mind is the superfluidity, because with the cold atom community, the first after this the BEC is to show the superfluidity behavior of this. So the superfluidity is if you have a quantum liquid heating into an object, if they are classical liquid, you see backscattering. If they are superfluid, you see frictionless flow across this object without backscattering. But that asks you to have a superfluidity condition that essentially the speed of sound of the system must be smaller so that you don't, in the Bogoliubov excitation spectrum, you don't excite other mode to dissipate your superfluidity energy. So indeed, there's some low temperature study back to 2009 with gallium arsenide system. Their sample, shows not as nice as the cold atom, but at least some of this behavior. But cold atom show this differently, show the vortex. I want to say that particle interaction in this system is critical. If we only have photon without interaction from the exciton, you wouldn't see any of the suppression of the superfluidity. It's just backscattering because they never form a superfluidity state by locking the particle together as one particle. So in our experiment, we have this cesium lead bromide really nicely grown here. It's a large sample, and one can control the polariton liquid injection by tilting the laser to resonantly inject into the cavity. So once we inject this at a really slow in-plane velocity, and by tuning the power of the incident particle density from below the Bose-Einstein condensate threshold to after the Bose-Einstein condensate threshold, we see the backscattering become dramatically suppressed. This is the experiment. This is our simulation. You see a little bit of scattering here. That's due to the superfluidity heating length physics. And the K-space also show before the superfluidity transition, there's a scattering ring. After the superfluidity transition, there's no scattering ring. Essentially, the scattering becomes fully suppressed. More interestingly is if you increase the superfluidity injection density, the injection density at the same time changing the angle to a little bit higher angle so that you break the speed of sound in the quantum fluid. What's going on is you no longer be able to form the superfluidity. Instead, you have this Cherenkov cone open up. So essentially, it's become a classical liquid, just like you have a jet that flow above the speed of sound. You see the linear wavefront open up. So we also see this. This is a fully observable transition. And then we can extract the exon-exon interaction by seeing this with different pump power, the angle how this open up. So we extract this is about 4 micron EV per micrometer square, a similar order as gallium arsenide or 2D material, but 100 times larger than organic. If you compare with our work with the room temperature previous attempt in the organic, you will see they never observe because they never observed the Cherenkov wave open up because the limited exciton-exciton interactions in the organic. Because in the organic, they are Franco exciton, very localized, not much interaction. Another interesting study one want to study with this as our system is to try to see the spin physics of it. There's a famous experiment in the gallium arsenide community using the XY Hamiltonian. We call this XY Hamiltonian simulator. So essentially by directly observing this interference pattern, one can extract the BEC condensate's phase. And from this phase, one can extract the XY spins configuration directly without complicated technique. So here we show, in the Nature Material paper, we show our solution growth cesium lead bromide shows really beautiful interference pattern, homogeneous. Compared with MBE grown gallium arsenide, they show more homogeneous even compared with our result. So this is considered, the first one that's really, surpassed the gallium arsenide case. I want to emphasize all of this condensate, theoretically, if you want to make the identical spin, you need to do feedback to maintain the amplitude of this everywhere the same. But in the gallium arsenide experiment, the solution grown, we never do this. Just because gallium arsenide didn't do this, we try to show this. We actually can do this at a better in a better case. So beside the construction XY spin Hamiltonian with spatial light modulator, another way to do this is by design a potential variations. Just like in the Schrodinger equation, you have potential, not only the particle density distribution, but also the potential is distributed. This is traditionally done in gallium arsenide by etching a really deep quantum well with high aspect ratio. And then that is not really easy achieved, especially once you're etching this with very small features. The defect on the edge start to quenching this quantum well behavior and make the experiment really hard to interpret. So one of our field's popular trial is to always to demonstrate a topological insulator. As we all know, topological insulator is one of the very exciting research topic, from the quantum Hall to quantum spin Hall to anomalous quantum Hall. Those are all, exciting discovery. And but condensed matter-wise, or from the physics-wise, to synthesize those materials is typically not easy. But due to the analogy of Maxwell equation and the Schrodinger equation, you can mapping this potential landscape into the refractive index landscape easily. So essentially that means instead of construct a complex, hard to grow material in your MBE machine, you easily just make the sample with a photonic crystal and start to patterning the refractive index and then to construct your artificial photonic topological insulator. So this idea indeed to inspire a lot of the work with a photonic topological insulator. For example, we have in this microwave regime back to 2009 by Professor Marin Sajuchi's MIT's group in this quantum Hall topological insulator. We also have this spin Hall effect with this photonic crystal by breaking this inversion symmetry. And this quantum anomalous Hall effect can also be constructed with a photonic ring structure, as demonstrated by this 2019 work. So there are, although there's many interesting proposal and experimental demonstration in the pure weakly coupling photonic system, people still want to demonstrate this with interactive photon in the polariton system for this topological insulator. So many of the theory back to 2015 even proposed to etch this pillar of this gallium arsenide or doped gallium arsenide system in theory, try to demonstrate the defect state being propagated without backscattering. Those are the theory work. There's some previous attempt try to realize the theory work of the quantum spin Hall effect. For example, in my colleague with the German Sven Hoflin's and Sebastian's group, they essentially with a doped quantum well system with a magnetic element in there, where they apply a strong magnetic field and eventually open up a tiny Zeeman response gap to break the time reversion symmetry and open the topological band gap. But because the band gap opening in there is only about 100 micro eV, so essentially it's too small, and due to the Zeeman effect. So you have to try to observe this at a low temperature, and in their experiment, because they dope the magnetic that's lower the cavity's Q factor, they never make the condensate into the topological band gap. So the condensate is always outside the band gap. You never construct the topological BEC inside the band gap to see this BEC propagate along this topological edge. And one can see this by a filtering process. You essentially apply a filter to see this upon condensation. Another interesting work is done by my colleague in UPenn with Anwar Ratish's group. So essentially they use 2D material with a photonic crystal, silicon nitride membrane, and then as we all know that 2D material never go to BEC, so they only see the polariton in the linear regime to see this spin up, spin down state go to different propagation. So there's no need for the magnetic field, but there's no topological condensate of BEC. So for our work, we got great inspiration from the topological valley Hall effect in the 2D material. So essentially, if in the graphene case, you break the spatial symmetry from the C6 to C3 symmetry, you will start to open up a two valley. And then in the condensed matter system, by pumping it, you can have a valley Hall effect, as shown in this experiment and theory. Such an analogy has been mapping into photonic by Professor Gernadi Shavas. And essentially, he designed a photonic graphene where you can see the left-handed circular polarized light and right-handed circular polarized light show same K space valley. But if you break the symmetry to make a larger atom and a smaller atom, you'll be essentially construct artificial MOS2 lattice So essentially, the left circular polarized light and right circular polarized light behave different, and you open a complete band gap for the topological state to emerge. So if you bring this two state into an edge state, you start to show they have different edge states start to show up. One we call this a B state, the other one we call this A state. The B state has two flat ends facing each other, has more confinement. And then if you calculate the chain number, one easily realize the chain number has different signs in the valleys in the valley. So inspired by that, we come into the Polaritron regime, carefully chosen the cesium-lead chloride system, and pattern our Polaritron system with large atom, small atom, and then construct our in-plane MOS2. And we chose to have the B state. So in this way, this topological edge state has more confinement. And here is the theory calculation. And we choose cesium-lead chloride simply because if you pattern the cesium-lead chloride, you see no damage. Oxygen plasma treatment, this MIBK, IPA development in the E-beam lithography never damaged the photoluminescence. This is a very robust material compared with our previous nature material work. So here we show with this design, one can show this really nice sample with pattern, with topological interface, and you pump at the topological interface, you see this topological mode start to emerge. And experimentally, one can map the EK relationship and directly visualize the topological edge by selectively pumping this area and see the EK diagram. So here is a simulation showing if we have topological edge states, this mode will be countering the C3 symmetry sharp turn without even losing a power. This is the simulation. And if you have, in the bulk mode, if you pump it, they start to just convert, just without even confined in the edge. So they gradually dissipate away. With this, we can selectively chosen to see different region to see the trivial mode and the topological mode. As you can see, the topological mode is matching our experiments, and then the bulk mode is gradually decay out, exactly match our simulation. So if you pump this topological system into the Polaritron condensate or Polaritron BEC, you will see they nicely form a two condensate, and then they show line width narrowing and non-linear increase and even blue shift. So that means our topological edge now, even though they are different location, but because everywhere is form a same condensate, same energy state, they behave like one particle. If you do interference pattern before condensation and after condensation, you will see after condensation, you see interference pattern everywhere. So we have a better sample here. You can see the interference pattern that is everywhere built up. And one can map the spatial coherence by extracting the G1 coherence. You can see this G1 coherence is everywhere start to build up. If you have the trivial bulk states, you only have the interference in the mirror symmetry because it's self-interference. So you never form a topological mode that one part of everywhere behave like one particle. So with this design, one can even make a more complicated geometry. Here with the fish, open the mouth, and the fish close the mouth. And the editor liked the idea and luckily chose our work as the cover for the Nature Nano technology. But on a little bit on the side story, my postdoc eventually, one designed pattern originally is flip 90 degree. It's like a tree. And then it's like a Stanford logo. Then I said, okay, you cannot design this. I'm a Berkeley graduate. You have to flip it 90 degree. So that's the whole story behind it. With that, I want to quickly summarize our work. I hope in the short period of time, I convince you in many aspects, cesium-based halide perovskite seem to be so far the best material for room temperature, Polaritron and the BEC physics study. And many groups are working on developing methods from growth and device fabrication to advance this perovskite Polaritron field. And our recent collaborative work on superfluidity, XY model, topological Polaritron build some of the landmark for future BEC and the Polaritron study at room temperature. With that, I want to thank my postdoc, Dr. Kai Peng, who made the most significant work, and he's now assistant professor at the Chinese Academy of Science, and also my graduate students, Mr. Wei Li, and also our collaborator at the Argonne National Lab, Dr. Da Fei Jin, previously at argon now at Notre Dame, and Dr. Han Xu, and Dr. Chaoyang T, and ONR and NSF for specific support for this project. With that, I want to thank for your attention and happy to answer any questions.
For your talk, if I understand the spectral system correctly, thank you. Thank you for your talk. If I understand these systems correctly, the coupling, I think of this as maybe overly simple, but the cavity basically captures light and you just get excitation, de-excitation, excitation, de-excitation over and over and again until you cannot quantum mechanically differentiate the light and the molecular. Did I hear you right that you were saying that one of the innovations here was the cavity? Because you can only do so much with the material. It has the properties it has, but these cavity quality factors really need to be extremely high. Like Q factors and like a whispering gallery mode can get to 10 to the 9. DBRs are significantly less. So what was am I interpreting this correctly? And if so, what was your cavity quality factors?
Yeah, that's a good question. I think for our cavity case, we are thousands, around thousands. But if you want to have thermodynamically a thermal equilibrium BEC, you need to have this quality factor about 1 million. So that every particle in there is thermalized. It's not a part of the particle is thermalized, the other particle is non-thermalized. So for our case, I think we mainly work in the regime. Many of the particles thermalized, but not all of them thermalized. So sometimes it's not fully a thermal equilibrium BEC, but a little bit non-equilibrium. You can see this. But on the other hand, you ask whether this Q factor is a dominancy. Yeah, from a condensate perspective, you don't need millions of Q or whisper gallery 10 to 9. You only need a few thousand. The reason behind it is to consider a material, it's a special laser, it's a gain, balance, loss. As long as your gain is sufficient, you can run into a nonlinear regime. So that's more than enough.
We had another question here.
Thank you for your talk. I was interested in, my recollection is as you increase the binding energy of these excitons, you also tend to localize them. So as from Vanier exciton to very localized exciton, is it playing a role there in the polariton state as well?
Yeah, so one of the observation in the field, that's a very excellent question. I didn't realize this, but one of the problem in the field is you can work with binding energy hundreds of MeV material from Franco exciton to why not mode, 2D material, or even layered perovskite. But those materials tend to have, because they are tightly bound by the exciton, so that means the exciton-exciton interaction become huge. So they tend to be annihilated. Once you really drive the system into nonlinear regime, you need a lot of exciton. But the exciton interaction, because the binding energy is large, also become large. So they tend to annihilate the quench without giving photon. So there's a right balance point. And related with the system, from our perspective, I think the cesium lead chloride, which shows about 60 MeV, 70 MeV, those are the right range of material to work. Based on the Saha equation, they have really good equilibrium. Majority of the particle are exciton. On the other hand, they don't have a really strong exciton-exciton interaction, eventually quench the polariton condensation.
Just a quick follow-up. Are you discovering anything interesting in terms of, of course, these allied perovskite are also used for PVs, and the recombination rate of exciton is one of the interesting physics. Are you learning anything about what's happening in PV by coupling to this nonlinear regime with light?
Yeah, that's a good question. So I think we basically, from our understanding, is you can see for the single crystal one. I never work with the polycrystal one. For the single crystal one, this is comparable with the Garnet arsenide. If you see the blue shift. So typical blue shift that before the condensation, you have a little bit larger blue shift, simply because if you have a defect density, they tend to be the trap in the below. So you start to feel the trap below and then shift the system's energy until there's no trap. You start to linearize to go to the second state. There's no trap. So essentially from this slope, you can extract the density of the so-called trap states for the exciton. So our conclusion is it's as good as the Gardner arsenal. So the quantum yield from our measurement is about 50% at room temperature.
Thank our speaker again.
Thank you.
The last speaker for break is Daniel Schumacher, speaking from the APS side on functional electronic materials on the verge of stability.
Okay.
Okay.
All right. So thank you a lot for having me. It's a pleasure to be here. I have organized the user meeting at Oak Ridge before as the chair of the user committee, so I know how much work it is, and I really appreciate Mingda, all the local staff, everyone putting the sessions together. It's a ton of work, but it's really important, and so this is like a meeting that's very dear to my heart. Also because this is where I was 11 years ago. There I'm hiding in the back. This is outside 223. This building is still there. So I was working with Mercuri Kanatsidi, so I was a postdoc there, and then here's Duck Young. And there's a lot of people who were really important to my growth as a scientist, and so being able to work in MSD and do experiments at the beamline was really special. And now I get to do it in my group at Illinois. And so I'm going to talk about a couple of different projects, especially work done here by Manohar and by Zach. And I'll hit a few different beamlines on the way. And we're supported by the NSF and Department of Energy through like QSQM, Energy Frontier Research Center, and some other projects. And so there's two things that I won't talk about today, but just to give you a flavor of what our lab does. We're in our inorganic materials lab, and we like to do a lot of synthesis at the beamline. And so this is when we took an entire hydrothermal oven and took it to John Okasinski's beamline, and we're growing a metastable copper oxide there. I think you'll hear actually probably like better work on material synthesis in the beamline from Karina, who's going after the coffee break. So hang in there. I know this like Cinco de Mayo themed lunch is pretty heavy right now, but we're gonna make it. We're almost to coffee break. And then we've also worked on HBCAT doing diamond anvil experiments on this chiral semiconductor. It's a really interesting compound. It's this silver gold selenide, and you can see the chirality of this silver chain in the structure. It's actually a cubic material, and so the chiral axes go in all three directions. And we were curious to see if you squeeze on it by about 9 GPa, you're actually supposed to collapse the band gap of this thing. And you could kind of tune the band gap all the way from a little less than an EV to being metallic. And it looks like that's actually what happens. And so we did the structural work here at Argonne, and then we did synchrotron IR at Brookhaven. But the two topics that I want to talk about today to showcase some of the things that we've done at APS are about terahertz. One is building terahertz devices, and one is trying to generate terahertz waves. And so the first one is about precision, so the precision that we get when we have synchrotron X-ray measurements. And this comes from the spintronic field, and there's this quirky material that I'll talk about, copper manganese arsenide. And there are a bunch of different groups who have made these devices where we have 4 contacts. And so you'll see these in papers. They either have 4 contacts or they'll have 8 contacts like a Union Jack. And the idea is that you're going to send non-spin polarized current through one direction, and then you're going to probe the voltage in the other direction. And you can flip 90 degrees every time you send a probe in horizontally, probe in vertically. And that's what's in this little schematic here. And so it's a non-spin polarized electron current going through. And when you do that, you are, in theory, flipping the domains, the magnetic domains of this material back and forth. And this is interesting because you can do it at picosecond timescales. And the second thing that we want to talk about today is looking at the dynamic range that we get from the synchrotron. And so we're looking at the complex charge density wave response of this material, tantalum selenium iodide. And so we'll look at this first magnetic project. And the reason why it's interesting is because ferromagnetic memory storage is everywhere. Almost all data storage is done in data centers with this technology. And there has not been a change in the maximum frequency that you can switch magnetic domains since like the 1950s. We came up with YIG garnet. You can also use ferrites. You can use metals. You top out at about 1 gigahertz, the fastest that you can switch domains left and right in this case. And that's the ferromagnetic resonance. Okay, if you have an antiferromagnet where the nearest neighbor exchange coupling causes these domains to be anti-aligned, then you essentially have a different speed limit. You get a fundamental frequency of about 1 terahertz. And so if you, in theory, have this 1 terahertz switchability, you should be able to do really fast writes in opposing directions. And you can imagine writing domains in an antiferromagnet like this, where again, in each domain we have net zero magnetization, but they're switched 90 degrees. And so can we store data this way? This is like the promise of these plus or Union Jack shaped devices. And the way that they've done these experiments is not our data, but what they're doing is they're sending a picosecond current pulse in, and this x-axis says pulse count. So they're sending pulses like this at kind of a slow rep rate, but each pulse itself is very fast. Okay, so we want to investigate if this is actually something that is feasible. What sort of materials would you use to build a technology on this? And so you need to have a few things. You have to have a nail temperature that's above 300 Kelvin, so you want this thing to work at room temperature. You need to have metallic conductivity because you need to be able to send the current in, you need to read it electrically. You have to have, this is a tricky one, must have the crystallographically equivalent axes. If I want to switch this thing 90 degrees, it has to be cubic, or I could switch it 60 degrees and have it be hexagonal, or I could be tetragonal, but that's it. Anything with lower symmetry than that, I don't have a 90 or a 60 degree symmetry that I can switch. And another thing that nature almost always works against you in is that the spins have to point along that degenerate axis. If it's tetragonal, the spins go along the c-axis, doesn't work. I can't flip it 90 degrees. So if you take these criteria and you kind of go through a big list of magnetic structures, you come up with like as many materials as you can count on your fingers, and they only are in a couple different structure types. There's the CuSb type, Cu2Sb type. Copper manganese arsenide is the one that we saw earlier, and then you can substitute both metal sites with iron or manganese. And then there's these intermetallics like Mn2Au and chromium-2 aluminum. That's just about it. Okay. And so you can build these devices and you can try to understand, okay, what do the antiferromagnetic domains actually look like? And so this is not our paper, this is someone doing XMLD PEEM of this switching experiment. And so the bright and dark spots that you see here are the domains. And they send the current in, and then they say, look at how the domains have switched. And you're like, are you sure? Like, you don't have to be like an expert in antiferromagnet domain imaging like the person who wrote the review article on it. Do you know who it is sitting in this room? He's smiling, it's Laurent right there. So you don't have to, you look at this and like, oh, okay, yeah, sure. There's like this little blob there where it's darker than it was before. I'm not sure that this is something that I want to build my next data center on, but yeah, you know, this is a 1 micron square, so these domains are really small. And there's some other energy scale, it seems like, that's pinning these domains. They can't just be flipping around in response to the applied current. And so that's what we wanted to understand. When we grow these materials, are they actually really tetragonal like they're supposed to be? Are they really degenerate? And are the magnetic structures actually well behaved? Do they flip around in the way that they're supposed to? Okay, and so we can look at the magnetic structures of these materials. So we'll take just a look at these 3 things that have the same structure type. They're all tetragonal, so the c-axis is pointing up and down. And the atoms with arrows on them are the magnetic ones. So this is copper manganese arsenide. It only has moments on the manganese. And it's like your happy antiferromagnet. It goes left, right, left, right. So this has a k equals 0 k vector. The way that people grow this in those devices is they do MBE. No one's ever made a single crystal of this, which as an experimentalist, I found that very strange. It's such an important material, no single crystals. Like, why is that? There's also iron 2 arsenide. It has this sort of triple block array. It goes left, 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 right, right, right. And so it has a magnetic cell that's twice as long. We've grown single crystal this. We've measured like inelastic neutron spectra of it. It works great. It's nothing like this one that we can't make crystals of. Mn2As has a similar magnetic structure. It's like a double block, doubled unit cell. This one makes single crystals too. And so since we're a material scientist, we like to make phase diagrams, and we would say, well, what systems are available? If I take these three elements, copper, manganese, and arsenic, the material that I want is right in the center. It should be a tetragonal material right in the middle of this triangle. But the few papers that are out there say that there's this big solid solution region that is all the way in this pink region, which usually is a good thing. That means that I can tune the properties. But the bad thing is that it makes competing phases, this orthorhombic one and a hexagonal one, that are really close to the center of the triangle. And they're not even structurally related. They have different coordinations of the manganese. And if you do high temperature calorimetry and you heat your sample up and cool it down, you see that it goes through a bunch of phase transitions. And we think this might be why it's hard to grow a single crystal of it. And so we made this material. We made a powder of it because that's what forms. And the first thing that you do is you take your best sample and you run it at 11 BM, which is the best, highest resolution powder diffractometer you can find. It's an awesome program. We get this data that's in black, we fit it in red, here's our difference curve in blue, and it looks pretty good. It's a magnetic material, so we took it to PowGen. There's a neutron diffractometer at Oak Ridge. Again, the fits look good, but when you're at APS, you do these fits, and the student or whoever comes, they're like, yeah, fit looks good, and you're like, really? Keep zooming in. Show it to me on a different scale. And when you're at APS, this is actually not a good fit. This is off a little bit to the side. It's got this teeny little shoulder on it. And these are the details that you absolutely cannot see at your home lab, right? It's only when you come to the synchrotron that you say, that thing's shifted a little bit. What's up with that? Is there some like alignment problem? No, the instrument is perfect. It's more perfect than your material. This is real, right? This is a problem with it. This is when your instrument scientist is like, no, that's your sample, man. Sorry. Your sample has that shoulder. It's not my shoulder, it's your shoulder. It's true. This is what the material does, okay? So once you see that, you're like, oh, I'm starting to understand why it's hard to make crystals of this material. So we took that data at room temperature at APS. It's a magnetic material, so we took it to PowGen, which is Ashvia's instrument. She's sitting right over here. This material is supposed to have a nail temperature at 400 Kelvin. So if we go above 400 Kelvin, we should see no magnetic peaks. This measurement that we're taking is at 500 Kelvin, and you see this big K00½ magnetic peak right here. If you look at the structural peak, which is actually the smaller one, and it's up in this inset right here, you can see that that thing is actually split. So at high temperature, this thing is slightly phase separated. It has a magnetic peak that's not supposed to be there, and this magnetic peak corresponds to Mn2As, which is like the end member phase. It's all the way on the edge of the triangle. And that thing has a nail temperature at 520. So that, in a way, makes sense, but this peak is not supposed to be in our sample. So it's obviously phase separated because we see two structural peaks. It must have an antiferromagnetic component in it, but it's got to have something else that's left over because there's two phases. A really strange thing happens when you measure the material when it's cooled down. The other fraction of it goes magnetic when you cool below 400. And when we're measuring at 300 Kelvin, the K0 peak shows up where it's supposed to be. So that's our second magnetic peak. And the peaks merge together, which is super weird. So we have this essentially one structural peak, and we have two magnetic peaks. And so we wanted to see what this looks like when it evolves. And the most important thing that you can see is the 11 BM data. So we had this high resolution data. The next thing we wanted to do was take it to higher temperature. And so we start at low temperature at 100K, heat it up to room temperature, which is right about here, and this is the 003 peak, so we're watching the C-axis. And as you heat it up, it actually starts splitting, and there's 3 peaks here, and it maintains these 3 peaks. In neutron diffraction, you see the same thing happening, but it doesn't have the resolution, so it kind of just looks like one peak going up and turning over. And in calorimetry, you can see that it has this thermal, like tabletop reaction happening, where it has a nail temperature up here at 400 Kelvin, and there's some weird transition happening right around room temperature. And so what it means is that this material, when I heat it, or if I apply current pulses, even at room temperature, I'm sitting inside a phase transition that's 100 Kelvin wide. And as soon as I put a heat pulse in it, it's going to start moving some of those atoms, and they're going to ratchet back and forth. And so we think that what's happening is that these materials are actually traversing a phase transformation after every little switch. And once you know that this is happening, then you go back to the TEM, and this is a dark field image, and then you can do an EDS mapping of the different elements. You see what's actually happening is the copper and manganese are phase separating. It looks like a shape memory alloy. It looks like something that we saw from additive manufacturing, right? It has this big tweed pattern, but these things are actually the same lattice parameter at room temperature. The phase transition is entirely driven by magnetism, which is very strange. It's just like a martensitic shape memory alloy, except it's antiferromagnet instead of ferromagnetic. And so for this material, we were wondering, are the magnetic structures well behaved? No. Do they obey our crystallographic constraints? Well, they're both these phases are tetragonal, but if I'm building like a nanoscale or even micron-sized device, all these stripes are now 2-dimensional. So I've broken that 90-degree symmetry, and it's not something where I think that you could build a functional like terahertz device out of it, because you're dealing with diffusion timescales. Okay, so there's some tricky things that have to happen in that material to turn it into like a viable terahertz technology. But the next thing that we want to look at is something that is intrinsic. So we're going to switch and look at materials where we have a different kind of like gapping, a different type of energy scale. And this all came from charge density waves. One of the leaders in charge density wave materials, like back in the 70s and 80s, was Jean Rouchel, sort of like the French analog of the people who are working on charge density waves here at Argonne, like Dave Hinks, Jim Jorgensen. All these people stopped working on charge density waves when high TC were discovered. They were all charge density wave people, and then they became cuprate people. And so if you think of a compound like NbSe3, we'll do like a little bit of materials chemistry here. Looking at the periodic table, you would think that it should be like Nb5 plus. And so you could write a valence precise formula for an insulator or a semiconductor that had a formula like Nb2Se5. This thing makes sense, like Ta2O5. If I add one selenium-selenium bond, so I make like a peroxide, like a perselenide bond, by connecting 2 of these, that would make something like Nb2Se4 and then 2 more. So that makes like 2 niobiums and 6 selenium, so NbSe3. That's how we can rationalize one of these things. I'm going to take an insulator, I'm going to add a bond, and you can see that bond because those atoms are actually like close together. It's actually a metal, this thing. If you look at the orbitals, you can see where the Fermi energy is, and it sits right in that dz squared like niobium orbital. And normally the question is, for a material that has a sparsely occupied conduction level, can I create a lattice distortion and create a gap? And so since these are kind of weak bonds, we'd expect this gap to be small. And this is a Peierls distortion. It should turn like a metal into an insulator. And so we could do this for NbSe3, and you look at the band structure of it, and you're like, oh, this works really well when I have one band, but now I have like too many niobium in this cell. This unit cell is just so complicated. And there's way too many of these bands that could distort. And even if I distort one of them, I still have like 5 more bands, and this thing is still going to be metallic. And that's exactly what you see. And so this is the resistivity of this thing. When you cool it down, the resistivity goes down like a metal. It has 2 charge density waves, but it's kind of like a metal to metal transition. It's just metal all the time. If you apply pressure to it, the charge density wave goes away. So it's just like this material that, like in the title, is kind of on the verge of stability. So we can mess with it and make it go away. But we would like something where it's a little bit more robust. They did, back in the 70s, they did some of the first electron diffraction work on it. You can see, you can't really see it, but I'll just tell you there's these teeny little superstructure peaks there. They're very weak. We have some advantages now. We have better probes. And there's a material that's actually much better for this. And so this material has a funky formula, but we're gonna work through it. This is tantalum selenium iodide. So the tantalums are in orange and the seleniums are in blue. If you look at one of the motifs, it looks like this. And so it has a tantalum in the center, and it has these selenium-selenium dimers around the outside. And so this one here, it looks like it has 4, but 2 of these are shared with a neighbor, right? So there's 1 tantalum, and for each tantalum, it has 2 selenium-2 dimers. Okay, so if we draw this way, this selenium-2 dimer should be 2-, and there's 2 of them, so that's 4. Tantalum should be 5+, so there's 1 d electron left over, okay? Okay, for every 2 of those units, I have 1 iodine, which means that the iodine is going to take half an electron away. So this dz squared orbital, like I could imagine that this thing would be like completely filled or completely empty. In this unit cell, I have 4 tantalums, and each one of them only has a half-filled dz squared orbital. This unit cell has the tantalums at 0, 1/4, 1/2, 0.75, and 1, so they're perfectly arranged in a chain. The seleniums that are going around the outside, you can see that I've drawn the bonds here in blue. So there's like a bond here, but there's no selenium-selenium bond here. There's a longer distance. And if you look down the chain, the bonds actually go down the c-axis like a corkscrew. And so this is a chiral material. Each one of the chains in the unit cell is going the same direction. Okay, and so we have this like 1/2 electron left over in something that can hold 2 electrons, so it's essentially like 1/4 filled. And there's 4 tantalums. And so what this is gonna do is we're gonna take like the dz squared orbital, which is a parabola, just like Wei had in his talk, like my fermion parabola. I'm going to fold it in half 2 times because there's 4 tantalums across the cell, and it's only 1/4 full. So that's what this is. This is my parabola getting kind of ping pong back and forth folded, and my Fermi energy should be right here, 1/4 of the way up. And the crazy thing is that if you do like DFT on this structure and you get the band structure, it has a Dirac point right there. It's just like the cartoon said it would be, there should be a Dirac point there. This is cool. It should be like graphene or something. It should be a metal, unless we gap it. So we'll grow these crystals. This is on a millimeter grid, so these are like 5 millimeters long. They're pretty hefty crystals. They're big enough for anything at the APS for sure. And when you measure the resistivity, we said that this thing should be a metal. It's not at all. That's weird. Start at room temperature, cool it down, and the resistivity is going up. And this is not just our samples. This is what the material has been doing since the 1970s. There's a CDW transition right around 250K, and it just keeps going up more and more. So this thing is like it's an insulator to insulator transition. Why is that? Because the band structure says it should be metallic here, and it should be metallic here. Okay. If you look at the charge density wave, this is, okay, we're giving a talk at the APS, so I apologize if you're not like a diffraction person, but this is one safe space where we can nerd out on like propagation vectors and stuff. So here's the Bragg peak in C, and this picture is from Alan Heeger's lab in 1985. So Alan Heeger got the Nobel Prize for polyacetylene conducting polymers. So they were also charge density wave people, right? And so it has this Bragg peak right here, and these are the first superstructure peaks. They have this weird K vector. It's 0.045, 0.045, 0.085, which is some kind of off diagonal direction. It's very strange because you would expect that the charge density wave should go right along the c-axis, right along that 1/4 Peierls distortion thing, but it's not. It's going off in some wacky direction. Okay, we took our samples, measured the Bragg peaks, a bunch of different places. We measured it at APS. This is like a big plot that came from SLAC. We see the same charge density wave peaks as everyone else over the last 40 years. We took these crystals to our chemistry lab, and each one of these rows is a single crystal data collection. We were actually curious about the chirality of it to see if they were mixed left and right, which they are. But every time we do a single crystal diffraction study, this is the iodine occupancy. All of them come back like 10% deficient in iodine. This is why the compound is actually insulating and not metallic. When you look at any given crystal structure, here's our ideal cell. The black atoms are the iodine. You can see the tantalum selenium chain right here. Just take one random crystal. We'll just take like the first one from the list. And what you can see is that the iodine is only partially occupied. It's maybe like 80% occupied. And some of the iodine is occupying these interstitial sites that are in between the other positions. Go to the next crystal. It has iodine that's maybe centered right here. It's not split into three. This one, it has a slightly different occupancy. But all of these things have the commonality that all of them have 10% deficiency in iodine. If you have 10% deficient iodine, that's going to drop your Fermi energy down, and it's going to cause a gap. Okay. This is what happens when you look at the Bragg scattering in sector 6. So this is our single crystal measurement here at APS. And you can see that you actually get a lot of diffuse intensity here. So this is at 120 Kelvin. It's in the charge density wave regime, but you see this scattering at room temperature too. And so what we're plotting here is the H and K directions. And so this is a slice normal to the C-axis in scattering. So we're far from the origin, L equals 8. And this scattering that you see, you can model this by looking at displacements that are the tantalum selenium, so those chains. If I give them a displacement along the C-axis and give them a propagation direction in HK plane, that's the only way to make this diffuse scattering appear. And this is not the same direction as the charge density wave, which was going off in a diagonal direction. This stuff also doesn't have the same temperature dependence as the charge density wave. And so this stuff is happening at all temperatures. It does change with temperature, so it seems like it's dynamic. And if we have these displacements, that also explains why we have iodine moving around in different places in the structure, and why we see gapping in our photo emission data. And if you have this stuff happening, it also means that your charge density wave, when you hit it with electric current or you hit it with light, that thing will move, but it will be pinned by the number of defects that you have. And so this material should have a really strongly pinned response of its charge density wave. And that should be uncommonly strong because we have an uncommon amount of defects and disorder in this system. And so this is what it looks like with just that modulation. Or just to give you some idea of what's happening, the blue and yellow atoms are kind of displacing along the C-axis, and that modulation is going in the HK plane. It has this kind of short modulation. It's completely unrelated to the charge density wave. It's going like √2 - 1, 1, 0 in that plane. If you try to look at this stuff in a regular diffractometer, even a modern diffractometer, not just like Alan Heger's system from 1985, if you take it to a really nice one from Rigaku or Brooker or like in the basement, here we're sitting just off the Bragg condition, so we're looking at this diffuse intensity. And this is our lab X-ray data, kind of normalized to the same Bragg intensity as what we get as sector 6. And this diffuse intensity that you see is just completely invisible. It's just not resolved at all in the lab X-ray data. And so you can't get diffuse scattering data that's meaningful. Even in this system, which has really strong displacements and just pervasive disorder everywhere, you really have to do it at the synchrotron to be able to get this knowledge. That's not the only direction where there is intensity. If you look at the angle sort of like 90 degrees, we'll flip this view of the diffuse scattering. So the diffuse scattering that we saw before, that previous figure, are these horizontal kind of dashed lines going through here where this blue arrow is. So our old diffuse scattering, I've like flipped it 90 degrees, and that's flat now in this plot. And then going up and down, this is the L direction, so looking along the C-axis. What we can see are these streaks. So there's a streak here, 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 anywhere where there's a yellow arrow. Like every Bragg peak has a streak along the L direction. And the only way to get this kind of uniform streaking in the L direction is by moving planes of atoms in the L direction. You have to take, in this case, all the iodines. It has to be iodines, because if you use the other atoms, it only gives you like every other peak. You take all the iodines, and if you randomly displace the planes along the C-axis, it'll give you this characteristic streaking kind of at every K index. And so what that represents is that we're taking iodines off this ideal site, and every once in a while, so in our model, we take 10% of them and just move them to the adjacent, now vacant site. And that produces this streaking intensity along L. So there's these two coexisting forms of disorder in this material. And we said that this should give you some sort of response. And so when we take these things together, we have this material that should be metallic. Here's the band structure. This is just from the ideal unit cell. If we move the Fermi energy down a little bit from losing 10% of my iodine, it'll drop down here. We pin the charge density wave. It essentially creates a gap here. We have papers on photo emission of this. If you'd like to see the gap, we can talk about it. But it basically gaps this thing by a very small amount, kind of like tens of MeV. And so now you have this thing that in resistivity we saw was like an insulator to insulator. And if you take this material, and we'll represent the material this way as having these black bars with a C-axis pointing this way, and hit it with light. I'm sorry, the light is green. I don't ever know like what color to make infrared light. It's not green light, it's 1030 nanometers. We'll hit it with 1030 nanometers. And there's nothing special about this experiment. Just hit it with 1030 nanometers, measure the light that comes off. And so this is done with our collaborator, Fahad Mahmoud, who's a terahertz spectroscopist and is all around optics expert. And look at what gets emitted by the material. So here, the material is sitting there. We hit it with the IR pulse right here. It can measure the terahertz response in two directions. So you'll measure the blue one, which is kind of normal to the chain propagation direction, the C-axis direction. And then the red one, which is along the C-axis. And what you see is that nothing really happens in the blue, you just get a blip. But in the red direction, along the C-axis, you have this really long-lived ringing that happens. It persists for a long time after the IR pulses hit it. And if you zoom out, you can see how long this thing takes. It's approaching like 100 picoseconds. If you Fourier transform it, then you get this peak coming out. This tells you like this frequency. This is happening at 0.23 terahertz. It's really sharp and really bright. There's no other material that gives such intense and narrow band terahertz emission as this one. And I think it's because there's no other material that has such a big charge density wave that is pinned so uniformly everywhere in the structure by all these defects. And it's amazing actually the material actually like holds together and is stabilized like that from different people making it in different labs. It always has the same charge density wave temperature. And so this brings up really outstanding questions that we have about how you can dope it, how uniform it is from place to place in the sample, and how universal it should be for other materials that have charge density waves, but basically like very high electrical resistance. I think if you have a high resistance in your CDW material, you may see something like this. Another funky thing about this material is that it's chiral, and we just don't know yet if the chirality is really necessary for this function. And so I wanted to wrap up with that story and just talk about the three, what I think are pillars for this user program, that we have really great capabilities. And so we said we can see this diffuse scattering because we have awesome signal to noise. We can move through samples quickly. We have really high sensitivities, and that lets us see things right off the bat and informs other measurements. Access is something that I think APS has done exceptionally well. So we use the mail-in program at 11BM for like the last 10 years, and it lets us get data right away so they can plan and get the next proposal written, right? When you're doing the proposal review, Aaron says, well, why haven't you done like mail-in at 11 p.m. yet? That's just like the first thing you should always do. And it's just awesome that it is like the default way for the community to solve really thorny structural problems. And then we all know that not all facilities do the people thing right? That's really what separates you having a nice beam time experience versus a bad one is the staff there. Are they gonna help you? Are they gonna help you after you leave? And the APS has always done a fantastic job for that. And so we have students leaving like this. And with staff right there. And so there's Matt there working with Meva from my group, just like working right alongside you. So it's a very special thing. And I think we saw like from the pandemic how hard it is to like lose that and then try to reboot it. And so for those reasons, I think the user meeting is especially important and is really a pleasure for me to be here. Be happy to talk with you later and take any questions. Thanks. I can hear you.
The crystallographic restriction you mentioned, cubic, tetragonal, is that actually due to the crystallographic symmetry? Is that actually due to the crystallographic symmetry? Or is it because if you normally the domains won't fit when this thing goes through the phase transition, and so you get domains showing which push on each other and there's energy issues. And if I had a monoclinic structure which was lattice constants 4, 4, 4, 90, 90, 90, would this still be an issue?
I see your question. I guess you could maybe get away with something that was lower symmetry, but those energies would still have to be equivalent. So if you really want it to be able to switch back and forth, it needs to be like reciprocal behavior. They have to be energetically equivalent. If you had something that was monoclinic, but it was like 90 degrees, but the unit cell was lower symmetry than that, I guess it would work if those two things are like degenerate in terms of energy. But I don't know that anyone has found that material, but if you have something in mind, I would be glad to hear about it.
Very nice presentation. I was curious, in the iodine compound, what if you made it intentionally 0.9 instead of 1? What do you think would happen?
I don't think it would change very much because these are grown in, from a practical standpoint, it's grown by chemical vapor transport. So you always have this reservoir of whatever the chemical potential is. If you want to change that, if you want to dope it, I think you need a fourth element in there. And so I think you can do it with niobium, but the crystals don't grow that nicely. So I think we can get like small crystals where we could do this, but because they're small, it's harder to do measurements on them. So we're working on it. But it's a really interesting idea, yeah. So the first part of the talk, it's not my device, and I would very much hesitate to call it a real terahertz device because it doesn't have a terahertz switching speed or a terahertz rep rate. It's a terahertz pulse, but the delay after that pulse is actually very long. So I think there's a lot of like wordplay going on in that community. It's electrical current. It's electrical current. And the current is high, very high.
For the second example, did you switch it, try to send circular instead of linear?
We haven't yet. We haven't yet. We know that these things are, every crystal is one chiral domain. So we should be able to get a chiral response. Yeah, we haven't done the terahertz response with chirality. They've just done like a circular polar galvanic effect. So they've done some other measurements that are polarized, but not the terahertz one. Yeah, it's an ongoing project. Yeah.
Okay, let's thank our speaker again.
Introduction. So it's my pleasure to be here. It's been many years since I've been at Argonne. We used to be frequent users about 10, 12 years ago. I think I graduated 2 generations of PhD students using the beamline for diamond anvil high pressure studies on materials. On this occasion, I would like to thank the organizers for inviting me, and I'll be speaking on some of our research on electronic systems and energy systems. So we work on 2-dimensional materials. No doubt many of you are familiar with this. I just show this slide usually for the students that may be relatively new in this field. These 2-dimensional materials, the most popular being the graphite system, can be understood as basically the equivalent of a stack of paper at the atomic level. So just like a stack of paper, you can peel one sheet from the stack. Likewise, this graphite system of carbon atoms hexagonally arranged, you can peel a single sheet of carbon atoms, aka graphene, from the parent crystal. So this now is a portfolio of materials that, according to the way you count it, can include hundreds of air-stable materials, and won the Nobel Prize for some physics studies about 15 years ago. These materials, even though they're experiencing what many call a renaissance, have actually been around for a very long time, even in terms of practical commodity uses. So the graphite pencils, the pencils that you have, are made from graphite. And it's because you can shed material from this crystal. That's how you can write on a piece of paper, basically exfoliating the material onto paper to print out your characters. So more recently, it's also been heavily used in battery systems. The other materials, HBN, for example, is an insulator. Boron nitride is very commonly used now in basically all cosmetics. So some of you that wear cosmetics, no doubt, are wearing HBN without you knowing it. And it's very useful because it's a dry lubricant, so it absorbs moisture from the skin, keeping the face looking very matte and dry, even during exercise. And then MOS2 is a semiconducting 2-dimensional material. It's commonly used as a lubricant, solid-state lubricant, in a variety of vehicles. So all these commodity or common applications take advantage of the tribological properties of these 2-dimensional materials. However, the billions of dollars in investments over the last 15 years are not to make a better foundation for cosmetics or better pencil. They're to really advance electronic nanotechnology applications. So within this portfolio of materials, you have basically every candidate in solid-state science, from superconductors to semiconductors and everything in between. So we have been very fortunate to have a multidisciplinary group from chemical engineering, from material science, mechanical engineering, and electronics to try to take advantage of the unique functions in this portfolio of materials and leverage them for new applications in bio, sensors, energy, optics, spin, and so on and so forth. In this particular talk, I'll just focus on our work on nanoelectronics and clean energy, but I'll be happy to talk to anybody on any of these other topics. So in terms of electronics, this is of course a huge space by itself. I'll mostly talk about memory or resistance change phenomena, which is a driving force today for electronic technologies. And the reason is the driving force is because of energy. If you look at the production of energy, global production of energy, it's increasing linearly per year. However, electronic systems, we're talking about ICT, cloud computing, mobile computing, laptops, communication systems, all of these have been growing exponentially over the last couple of decades. To the point now that the semiconductor industry are now projecting that if nothing is done, almost all the energy of the world will be consumed just by electronic technologies. So it's not a sustainable future. That is why there's a lot of effort and investment in energy efficient electronics to bring down this curve towards the fundamental limit of electronic operation, which is known as the Landauer limit. So you can see there's orders and orders of magnitude of opportunity to make electronic systems or electronic primitives much more efficient. So why is electronic systems today very energy hungry? There are a couple of reasons. At the device level, at the architecture level, the main reason is because information has to be shuttled between the compute center and the memory unit. So when we say this, we find that it's often very abstract for people to understand what this means. This is a so-called von Neumann architecture. So I like to use the analogy, I lived in California, the Bay Area for 10 years. I like to use the analogy of the Golden Gate Bridge. So in the Golden Gate Bridge, you have a lot of people that walk in the San Francisco, the island. You have a gazillions number of people. And many of them live in the mainland, San Mateo. I used to live in the mainland. And you also have gazillion number of houses. Unfortunately, you don't have gazillion bridges to bring people from the mainland to the island and vice versa. You only have one bridge. So one bridge serving gazillion people is not an efficient method. That is why this bridge, if you look at it now, it's not reflective of the situation. It shows like there's no traffic. But I can assure you, if you go to the Bay Area, this is jam-packed during rush hour. This is basically what is going on in computer architecture. You have gazillion processing information from the CPU, a lot of instructions, and then they need to access data from the memory. And you have gazillion, hundreds of gigabytes or terabytes of data storage, but the connections, the bus that connects this memory to the compute, you don't have that many of them. So then this calls for a need for a new architecture. So in the case of the Bay Bridge, the way to solve this problem is either have a lot of bridges, but there's no space, as you see, there's the ocean, or you develop a new culture where people live and work together. So for example, now there's a lot of housing developments, affordable housing in the San Francisco, so that people can live and work there, and then you can defeat this commute problem. In terms of architecture for electronic systems, the way to solve it is to move towards so-called brain-inspired architecture, so-called neuromorphic computing, similar to the way living brain is constructed, where you have compute functions, so-called neurons. You could have gazillions of them, and you have gazillion interconnections in this architecture. So there is no rate limiting step, so to speak. So this is exactly what many of us in the community and many folks here at Argonne are also working on to realize this kind of primitives, synapse neurons, using solid state materials and convert that to computer architecture. So I'll mostly speak from the device level, the primitives. There are many ways to realize this so-called synapses. Synapses are the most important. If you can do synapses, you can do neurons. There are many primitives to realize synapses. There's the flash memory, which is in your USB drives, and then the ferroelectric phase change materials. There's electrolytes and metal oxides. The latter two are often colloquially called memristos because you can toggle the resistance of these materials. So I'll briefly talk about the physics of these memristos. The metal oxide in particular is arguably the most or the leading candidate in terms of realizing the synapses that can be translated to industrial technology. So these metal oxide memristos are actually very simple. We learn about this in Physics 101. They're basically a parallel plate capacitor where you have a metal oxide that is not conducting and then a bottom metal. And so from parallel plate physics, you learn that this kind of construction does not have any current flow, vertical current flow from top to bottom. And that is the end of the story if you were in a university that are like similar to where I went. They said, that's it, you just need to know the capacitance and let's move on to other subjects. It turns out that that is not it. There's a lot to say about this kind of construction beyond just that it doesn't have current. In particular, it can allow current to flow, charge transport. And the analogy I like to give is the lightning effect. So if we think of lightning, we can think of the sky as a top electrode. The air around us obviously is not conducting any electricity, and the earth is the bottom electrode. But under some special conditions, you can have current flowing from the sky to the earth, lightning effect. This same physics can be observed in solid-state materials. Essentially, it's a high field phenomena. You have to apply a high electric field that leads to, in the case of metal oxides, that leads to the oxygen being released from its bondage to the metal, leaving behind metal, charged metal states, and then these charged metal states can conduct electrical current from the top to the bottom, which you can measure. So this phenomena has been observed several decades ago, and in the beginning, they could cycle this, actually go from on to off a few hundred times, unlike lightning, where we don't have control of this, despite the best effort of Nikola Tesla, who did research on controlling this. But in solid-state materials, you can control it hundreds of times of cycling in the early days. Nowadays, in some of the most advanced metal oxides, you can get even 1 billion cycles. So this is a real effect. As with everything, we want to make them smaller in electronics. This is the language of the semiconductors. Smaller is better. And for obvious reasons, which include that you can get higher densities. So if you want to do so-called brain-inspired computing, you want to emulate densities that are close to the brain so you can do complex functions like generative AI. It's going to be lower energy because matter needs to travel a shorter distance if you make it thinner. And it's going to be faster switching because, again, matter is traveling over a smaller length scale. However, we also know in semiconductors that there's no free lunch, which is the NFL policy. There's always going to be some challenges, otherwise there's no need to do research. And so some of the challenges are that when you make these sandwiches smaller, you can get leakage, uncontrolled leakage phenomena, current just flowing. So you lose this on-off ratio, you lose this ability to cycle this. And the main reason in the case of metal oxide is because when these materials are made, they are disordered materials, typically amorphous materials, at best nanocrystalline. So when you make them like few nanometers, there's a lot of pinholes, and this then destroys the observation of this phenomena. So we said, okay, the community is trying to make this kind of sandwiches very small. How can we solve this problem? This is where the two-dimensional materials come into play. These are the thinnest, smallest materials in the world. So we said, okay, let's see whether these materials can address this problem. We have HBN and we have TMDs that are insulating. So let's make sandwiches of these materials. And I was very fortunate. I had a gifted student who was in our first year at that time. And in my group, the first year students always work on high-risk projects that will probably not work. but it's also emotionally important to have something that works so you can get results at the end of the year. So this was the high-risk project. I said, don't worry if it doesn't work. In America, your PhD takes at least 5 or 6 years. You still have 4 years left, even if you spend 1 year. And she took my advice to heart, but in this particular case, it did work. So I said, try it. 6 months later, she came back with this sandwich of gold, MOS2 gold, showing the first resistive switching phenomena in this layered vertical sandwiches. And so these are typical IV curves. You have current on the y-axis, voltage. You see initially at low voltage, there's no current flowing. Then suddenly the current shoots up. This is the lightning effect. So typical breakdown field, not really breakdown, but high field is about 1 volt per nanometer. And then you see many orders of magnitude increase in current. And when you turn it off, it remains in that state. So it's a non-volatile, very energy efficient. And then you can cycle it back to the off state by applying the opposite polarity. So this is known as bipolar memory effect. Initially, when we started studying this, actually, one of my collaborators is one of the universities in Chicago. They said, oh, we don't know if this is true because you're growing the material. Maybe there's some kind of strange stuff with your material. So we decided, okay, let's reach out to all the best material scientists in the world growing these materials, in this particular case, MOS2, and all the best growers sent us their samples, and all of these samples show the same phenomena. So we declared that it's an intrinsic phenomena in this material, and we labeled it atom ristors, means atomically thin memristors. It's just the branding name. So going back to the science, the question that now emerged, especially when we submitted our early work for review, is we got heavily criticized because we didn't really understand the mechanism. We could only hypothesize. We said, relax, folks, just give us time. It's not like you solve everything in one night. It takes time to do the research. They're like, you don't understand it, it's not worthy of publication. So we said, okay, how do we understand this mechanism? So I know in the field of oxides and the field of solid electrolytes, defects play a fundamental role in the phenomena of resistive switching. So we thought, okay, maybe defects are playing a role here. So in the case of MOS2, sulfur vacancy is the most abundant defect if you look at the formation energy compared to other defects present in the material. So we said, okay, let's probe these vacancy defects and see if they show this phenomena. How do you go about probing this? You can use at the atomic level STM or TEM. TEM is very difficult to do in situ measurement. So we said, okay, let's do STM. The only problem is I am actually not an STM person. So I just had the idea, I scratched my head, and just like I'm giving a talk today, I was literally giving a talk at Oak Ridge National Lab and complaining about my lack of STM expertise and my need for one. And the group leader there, An Ping, said, oh, I have a postdoc, you can hire him, he's looking for a position. So just like that, monies fell from the Department of State, which was good times at that time. And I hired this postdoc, Seban, and he conducted STM experiments to try to elucidate the mechanism. The idea is to use triple mode capability available there, which is we can do atomic imaging, which everybody does for their samples. We can do spectroscopy, look at the density of states and so on. Everybody can do that as well. But in their particular case, the STM tip can also be used. They have multi-probe STM. You can do transport measurements, land the STM tip and emulate an electrode like you do when you measure devices at the macro scale. So we wanted to do all of this at the same defect so that we can fully understand whether the defect is playing a role in the mechanism. So you can always find a clean area even in a very dirty sample. So this is very clean. This is publication worthy. So we said, okay, this is clean area, no defect. Let's land the probe tip, STM tip on one of these exposed sulfur atoms of the MOS2 on gold. And we see nothing unusual. It's just ordinary IV curves, so nothing to jump up about. And then we said, let's find defects. And also, even in the very best samples, you can always find defects. It's thermodynamically guaranteed. So we searched for missing atoms. So these circles highlight 2 vacancy defects. So we said, okay, let's pack it on one of these defects and then do transport. And so in the transport, we can now see this hysteresis, so-called butterfly curve, that reflects the presence of resistance switching effect or memristors. But it turns out that the defect alone is not sufficient to produce this effect. You need interaction with the electrode. So I'll just highlight the mechanism through these illustrations where we thought, okay, maybe an atom from the electrode is being absorbed at this defect. So we can find a defect, a vacancy defect, apply an electric field with the STM tip, switch it from the off to the on state. And then our hypothesis was that the gold, in this case, this was gold STM tip, a gold atom from the STM tip was getting absorbed at the vacancy. If that is the case, we should be able to then image it exactly at the same point in the same experimental setup. And so when we do the imaging, we can see this bright protrusion. Geometrical analysis of the protrusion, the dimensions are consistent with that of gold atom. And then we said, let's do the reverse. Let's apply the opposite electric field. So when we apply the opposite electric field now in contact mode in STM, we can go from on to off. And then if our hypothesis is true, the gold atom should dissolve and we should recover the original vacancy. So when we do imaging, indeed, that is exactly what we see. So based on this, we can conclude with this mechanistic picture where you have a missing sulfur atom, a vacancy in this material. The vacancy itself is not conductive. So if you do STS spectroscopy, you see the pristine one is the blue one. The vacancy curve is very similar. You have a band gap. When you do measurements, there's no current flowing. But then when you apply a high field, an atom gets absorbed at that vacancy. And then when you measure the current can flow. And when you do STS, you now see you have a finite density of states, which means that that metal ion brings local conductivity to that point. So this is all done from those studies. These are very difficult measurements to do, at least for us it was. We spent 2.5 years and did this 5 or 6 times, so these are repeatable. And so this is the mechanism. And so now we asked ourselves, if this exists in MOS2, which is a typical member of the 2D family, does the same phenomena exist in all the other 2D materials? So far, the answer turns out to be yes. All the metal sulfides we could find all show this memristor curves. Metal selenides all show the memristor curves. Tellurides, heterostructures, and the world record, which we're filing, for the thinnest memristor resistance change in the world, hexagonal boron nitride, just 0.3 nanometers thin. These materials, those who work in 2D materials know that these are very flexible materials. In terms of retention, that's one of the performance characteristics. How long does it remain in a state when you remove the power? We can say that it's indefinite. We don't know how long. The students have tested it for a week and they said, oh, we're tired. We cannot continue to monitor the lab. So we can say with confidence that this lasts indefinitely. The switching time and energy are very, very small. We've not reached the limit. We can go below a nanosecond and about 50 picojoules. Those are the limits set by the measurement equipment. We still haven't found access to an advanced tool that can go below these numbers. And because these materials are very soft, you can place them on any substrate, plastics, glass, polymers, and you can bend them, and they're very robust and maintain their state. The case of HBN is very extraordinary because this is just one monolayer, 0.3 nanometers, and in this material, you can get 10, 11, and more recently, 12 orders of magnitude change of resistance in a single monolayer of HBN. Everybody is always surprised when I show them this. And you can switch this as low as 0.2 volts, depending on how much current you want this device to provide. And in the early days, a few years ago, when I used to present this, especially at the MRS or some industry conference, I'll show the endurance, which means how many times can you cycle this phenomena. It's very important for practical application from the industrial point of view. And in those days, like even a few years ago, 2021, I would show 200 cycles and people would giggle in the room because those were numbers that you should be ashamed to share. And I told them, just relax, it's just a matter of engineering to improve the endurance. It's not fundamental. But the industry is always looking for, we'll give you funding and you solve all our problems tomorrow night. But it takes years. So we said, let's just give us time. And now we can get over 1 million cycles in a single monolayer of HBN, which is just absolutely remarkable. And now we think we can get to 1 billion cycles of this phenomenon, which would be extraordinary. So in terms of benchmarking, we use power as a proxy for energy. So energy efficiency is the most important in terms of function in devices. So you can reset this HBN, set them extremely low power compared to other 2D materials and even other oxides or other electrolytes. So a lot of opportunity there for low power neuromorphic computing, especially for AI. There are many applications of this memory devices which I won't talk about. Of course, everybody knows that you use memory for storage. So those are just digital states, resistance, one resistance that is high, the other is low. Those are your storage primitives. You can also use them for computing. As I mentioned, there's this great interest in brain-inspired neuromorphic computing for AI. There you need analog changes in the resistance, not binary levels, but many levels, maybe 1,000 levels, for example, so you can emulate the functions of forgetting and remembering, which are the fundamental functions in neuromorphic. You can use them for security because sometimes these states are not stable. You can operate them in a regime where it's metastable. So you can use that then as a source of entropy for random number generation. And so we have a paper coming out on this. We've published already on this as well. And you can also use them for communication. So in fact, some of the early work was funded by aerospace companies interested in communication, where in those cases, you want extremely low resistance, very high frequency operation. If anybody is interested in any of these applications, I can talk offline about this. But for the sake of time, I'll move on to the second topic, which is a more recent topic for us, which is on energy. Particularly clean energy, hydrogen clean energy is a very important topic in the past couple of years, and this has to do with ion transport. So many of us come from electron transport, and ion transport is very similar, though it's distinct in its own right. So all of this clean energy utilize ion transport for one reason or the other. So you could have material assemblies that can be used as fuel cells. In that case, chemical reactions are used to generate electricity, which you can use for long-range vehicles, which is actually what started. A company came to us, they emailed us from the code, a car company, they're like, we're going to fund you to develop 2D materials for hydrogen fuel cells. But you can also use these similar constructions as electrolyzers, for example, for water splitting, to generate clean hydrogen or green hydrogen. You can clearly also use membranes for battery separators, for standard batteries, for standard electric vehicles. So in these membranes, which are the elementary devices in this ion transport, balancing adequate transport is extremely important with balancing separation. And I'll speak about that very briefly. So in our work, we've mostly focused on fuel cells. How do we address some of the challenges in fuel cells? I know some of you are, of course, experts on fuel cells. But for those of you not familiar, I find this video, which I show in my class, to be very useful. So these fuel cells are based on proton exchange membranes, and this illustrates the transport of hydrogen gas, generation of protons from a catalyst, and the transport of the protons through the membrane. And then it recombines with oxygen, and the output is water. So very, very clean. There's no combustion, no toxic gases, no need to capture carbon. So we said, okay, let's focus on this and improve this membrane science. The basic redox reaction is shown here. So at the anode, you have oxidation that produces charge. And then at the cathode, the charge and the protons recombine with oxygen to form water. So ideally, you get about 1.2 volts from this kind of fuel cells. Of course, you can stack the fuel cells and get more voltage, but each elementary cell gives about 1.2 volts. And this drawing here is quite complicated, but shows a variety of the species involved here. So you have hydrogen at the anode, which could come in as liquefied hydrogen, come in as a gas. Then that produces proton through the catalyst process. And then these protons travel through, and then they recombine. However, the picture is not perfect. Not all of the hydrogen gas that comes in, the H2, generates or produces a proton. That process is not 100% efficient. So you have some hydrogen that so-called crosses over to the other side, the cathode. And this is very bad for many reasons. It reduces the efficiency of the fuel cell, but more importantly, it reduces the durability. So this hydrogen fuel cells, the vision is that it's going to power long distance trucks. So for this kind of application, durability is extremely important. So we said, okay, how can we address this? So the two key metrics we have to focus on is proton conductivity. You want this to be as high as possible. At the same time, you want to block gas transport, which typically is in the form of hydrogen crossover. So the way it's done for prototypical electric vehicles is, like, for example, the Toyota Mirai, which is made in Japan. If your crossover is too much, what you have to do is you have to increase the membrane thickness and create a longer path length for transport. Unfortunately, that also couples with the proton resistivity. So if you make your membrane thicker, then the proton is also, resistance is also going to increase. So you have this trade-off. And so there's been a great interest then to see, can we bring in new materials that can help alleviate this trade-off? So 2D layers have been attracting interest for the last 14, 15 years as materials to include in membranes for all sorts of ion transport. So in this particular case, the 2D material itself is very fragile at a macroscopic level, especially if you're dealing with monolayers or few layers. So the idea is to sandwich them as part of a standard cell. The standard cell is typically made from Nafion. More recently, Gore-Tex is producing this proton exchange membrane. And so you have this interfacial layer, which is a 2D material with the goal that it will block the gas transport in the form of hydrogen, but allow protons to travel. However, the initial publications or reports on the proton conductivity of 2D materials was very, very discouraging. So this is work by Hugh and others. And their result actually is better than the first result. The first result by Andrew Geim, the Nobel laureate on perfect graphene, hydrogen never travels, can never penetrate graphene proton. So it would take years to get one proton to even cross it. So that was even more depressing. So these results are due to the fact that pristine 2D materials have over a small size, have no vacancies. There's really no way for protons to travel unless the pore is big enough. And most of the 2D materials, the pore is very small. So protons is very, very difficult to penetrate. So the proton conductivity here, in maximum 100 millisiemens per centimeter squared, is 2 orders of magnitude less than that of the Nafion polymer. So it's absolutely not acceptable to use this. But then the idea came about that perhaps that's because these materials are perfect. What if you have disorder in the materials? So if you synthesize polycrystalline materials, they have a lot of grain boundaries, they have point defects. Maybe that disorder can facilitate proton transport. This is in fact exactly what happens. So if you look now, the aerial conductance here is, you're getting up to 50, it's 2 to 3 orders of magnitude higher in pristine, in polycrystalline 2D materials compared to pristine single crystal 2D materials. So we said, okay, that's promising. This is a study that we did examining a variety of 2D materials grown by different processes. And then we looked at the crossover ratio. You know, you want very high proton conductivity, very low crossover, hydrogen crossover. So this ratio combines both metrics, and we see that graphene, MOS2 all show superior performance compared to the baseline. But then my student said, you know what, my student is very entrepreneurial, he's graduating this summer before the next student takes over. And he's always advising small companies, small startups, you know, on real technologies. Like, you know, even if we get perfect results, this is never going to be a real technology because in this process, we have to transfer the 2D material onto the polymer. And that process is not very scalable at a cost-affordable price point. So he said, you know, we can do the best science and we can all go home and be happy, but no company is going to pick this up. And I said, okay, what do you want to do? What should we do? He's like, the only way is if we can directly deposit on the polymer. I'm like, it's not easy to grow 2D materials directly at low temperature. Fortunately, just like I'm giving this talk, I was giving a talk at Rice, and iGiant said, I can deposit boron nitride at room temperature using pulse laser deposition. If that is your problem, just give me your sample. And lo and behold, we sent the samples to iGiant at Rice. And this pulse laser deposition, they use a 248 nanometer laser, ablate a boron nitrogen target, and then this fume then condenses on the, you know, your substrate. In this case, it's a polymer. So indeed, they could deposit this. This picture here is very nice. This is a TEM cross-section. These are amorphous or most likely nanocrystalline materials. They're certainly not polycrystalline or single crystal. And because the pulse has some energy, the condensation onto the substrate is of high energy particles. So what that means is not everything is at the surface. Some of this boron and nitrogen species, the radicals especially, penetrate the diaphion, and so you have a subfacial layer, which is shown by this XPS study. So penetration depth of about 50 nanometer. So we said, okay, let's test these materials, and indeed, unlike other work in which you can reduce the crossover by putting any 2D material on any polymer, but you also reduce the conductivity, this trade-off I talked about. In this particular work, we can reduce the crossover by about 30-35%, which is very good. At the same time, we can increase the conductivity. So that has not been observed before. And this remains something that is a puzzle that we continue to study. We understand that the 2D material will block the gas, so that's not surprising, but why is the proton conductivity improved? So we observed in TEM studies that there's a small thinning effect of the membrane, so then that would lead to higher proton conductivity. Theoretical calculations by our colleague, Professor Aluru, who was at UIUC and came to Texas a few years ago, shows that actually when you have these boron nitrogen radicals penetrating the polymer, they can functionalize and latch onto the side chains of the polymer. And that side chain can increase the diffusivity of hydronium. So protons transport through materials through hopping, so-called Grotthus mechanism, as a hydronium particle. So then this is a theoretical reason why this conductivity can increase. For the sake of time, I'll wrap up now. So the current approach to hydrogen fuel cells, or indeed any fuel cell using membrane, using discrete interfacial layers, is reaching a performance ceiling. Like there's only so much you can get from these interfacial combinations of material. What is needed now is to actually make new polymers, perhaps mixing polymers with 2D materials, with mexines, and creating targeted composites that can deliver both high conductivity and block crossover of whatever species necessary. And then for the electronic side, I spoke on this memristas, but I gave you a very narrow view. Actually, there's a lot of physics of interest that this kind of facility can advance. So the big question is the energetics. How much energy does it take for an atom to be absorbed in a vacancy? Because that's the mechanism for switching. So that question remains an open question. We know the limit is the Landau limit, which is a thermodynamic limit, about 3 zeptojoules at room temperature. How close can we get to that? So we need new technologies to do those kind of measurements. How fast can this switching operation occur? That remains an open question. I keep asking people, can we run the STM in open loop at femtosecond? And I'm told that's not possible. Then the entropy for the defense and military applications, they're very interested in this. We have a grant actually on that. Like, how random is this entropy, when it's in this metastable state of absorption, desorption? Because that's very fundamental to this kind of security applications. So with that, I'll conclude and thank a variety of sponsors and the students. So thank you all for your time.
Okay, time for one or perhaps two very quick questions.
No, thank you for the presentation. So about the first work you showed us, two quick questions. I think you must have studied different types of electrodes, right? Like gold, maybe different metals like aluminum. Do you see an effect of the metal? And also, is it only one defect getting filled is giving you the whole response, or you think multiple defects are getting, vacancies are getting maybe filled by them? Like, can you estimate that?
Yeah, so all this phenomena is present with any electrode. Most of the results I showed are with gold, but as you mentioned, we've tried copper, nickel, platinum, silver, we've even tried graphene. All of them show this phenomena. We just chose gold in the beginning because we wanted to rule out oxides. So gold being a noble metal, then we could rule out metal oxide formation. In terms of vacancies, of course, at the device level, you have a concentration of vacancies, maybe 10 to the 11 or 10 to the 10 per centimeter squared. And how many vacancies are filled depends on the compliance current. So if you see here, this IV curve, this current here is flat. It's not flat because it wants to be flat. We set it to be to prevent the device from damage. Because if you don't have a compliance current, you go from resistance switching physics to breakdown physics. The material breaks down. So how many of these vacancies are so-called activated depends on how much current you've set as your compliance limit. If you set very, very low values, like I showed for the case of HBN, sorry, I don't know where it is again, then you only have few defects. If you set very high values, then you have more and more of those vacancies occupied. Yeah, thank you.
Okay, let's thank our speaker again.
Yes, thank you all for your time.
Our final talk for today is Karina Chapman from SUNY Stony Brook. This is the APS keynote presentation, and she's talking about X-ray visions and focus.
Okay, I'm not really sure what that black box is. Maybe it'll go away by itself. Okay. Well, anyway, thank you so much to the organizers for having me here today. It really means a lot to me to be back here at the APS. APS has played such an influential role in my career and in my personal life. And so it just really means a lot to me to be here with you today. So when I first came to the APS, I came here by chance. I was 21 years old and I was 3 months into my graduate research. And I was just absolutely blown away by the amazing things that the X-ray beams here were telling me about my materials. And the fact that, you could, any experiment that you could imagine, you could make that happen. And so I went home to my research advisor, and I was pretty shy and not likely to speak up. And I said, I need to do more of this. I need to change my project. I want to keep doing this type of science. And that's exactly what I did. And so today I'm going to tell you about some of the most recent work that we've been doing in my group at Stony Brook. And some of the underlying motivation for this does come from that 21-year-old graduate student who was in the lab trying to make materials to do things and failing wildly. And so the work that we've been doing most recently is trying to understand the science of material synthesis. So what's the nature of the reactions that will give us new functional materials that are going to go into our energy technologies? And we now use our bright X-rays that we get at the APS to watch these reactions as they're happening. And particularly we're looking at the kinetics. And we're looking at how the kinetics change and how they depend on the chemistries of the systems. And that kinetic information tells us something about the rate limiting steps for those reactions. So it tells us about the key mechanistic steps, which is what we need to understand if we're going to design reactions to deliver new materials.
You're still on your intro slide.
And I hit a button and it didn't go. Okay. And I'm going to move this somewhere else, or maybe minimize it. I am going to restart this. Okay. Oh. Thank you. Okay, so the underlying motivation for trying to understand the science of inorganic material synthesis is that when you get truly transformative changes in energy technologies, so that might be a battery that's going to last 5 times longer, or a solar energy conversion material that's like 10 times more efficient, this fundamentally comes from the discovery of new materials that are incorporated into those technologies. And right now we can predict, we can grow on paper, on a computer, we can draw out different materials that don't exist yet, we can predict that they should be stable. We can predict what their properties could be. Computational materials scientists can go, this. You should go into your lab and make this. But what we can't do, and what they can't tell us, is exactly how to synthesize that. Because the synthesis process itself involves non-equilibrium transformations in chemistry, in structure that span multiple length scales. And so the way that we approach synthesis, and I don't know why this is not advancing. Let me try. Okay, that's very slow. So we do synthesis, material synthesis and discovery in much the same way that we've done for the last 20 years. 20 years, 50 years, 200 years. We take some kind of guess, we choose some kind of conditions, we run that reaction, we look at what we made. Is it what we were trying to make? Mostly no. And we go around in this merry-go-round of death. And occasionally you pop up and you made something new. As a graduate student, I was going around this loop endlessly, but experienced researchers, they can maybe do it a couple of times before they make their new material, and that's because they're guided by intuition. which just means that there's fundamental underlying science that we haven't quite understood and codified yet, and we can't apply it in a broad setting. And so this is the challenge that we've been facing and we've been trying to address as part of this next generation synthesis center that we've had based at Stony Brook. And so our goal is to use bright X-ray beams to watch reactions as they're happening, to understand the mechanism and the rate limiting steps, so we can design reactions in order to target those materials that the computational materials scientists have told us this is what you should make. And so we're trying to understand what are those key knobs that go into that reaction, and ultimately, if we can use the measurements themselves, tune our conditions live in situ in the X-ray beam in order to drive to that next material. And so I'm going to be talking about a couple of the different ways that we go about synthesizing materials in the lab. First is solid-state synthesis. So solid-state synthesis is where you take a couple of your precursor powders, you mix them together, you put them in the oven, and you heat it. You heat it overnight, you heat it over the weekend, you heat it for weeks, you heat it for long periods of time. And the reason for this is because in the solid state, atoms are effectively fixed. And so in order for the reaction to happen, you have to have diffusion. And so by heating it up, you're increasing the mobility of atoms and you're forcing transport to happen. So solid state reactions are inherently transport limited. But of course, there's a trade-off in everything, and as you heat it up, what you end up doing, and you're driving the reaction forward, you're getting transport, but what you're also tending to do is drive the material towards the thermodynamic minimum state. So if we're thinking about SiO2 phases, that means you're driving it towards quartz, as opposed to forming something that's really useful, like a zeolite, which every drop of gasoline will see. And so all these really useful materials that we haven't discovered yet, they're not the ones at the thermodynamic minimum. These are these metastable phases where we have to find the right balance of temperature and reaction pathway in order to isolate it. And so, how can we get these reactions to go to completion at a lower temperature where we might be stabilizing these metastable, interesting phases? And so, I know there's a lot of chemists in the audience, so here's our reaction mechanisms, the way we can think about solid-state reactions. Effectively, we've got precursors, we break bonds, we move all our atoms around, and then we remake our bonds. The part that's common to every single solid-state reaction is that movement part. Ooh. And so if we want to do something that's sort of generalizable, we can start ask ourselves questions about what's the role of transport limits in those reactions? And we can do this simple toy reaction, which would be ion exchange. So effectively, if we have ion exchange, the host lattice remains the same. So we're not, that bond breaking and bond making part, that's not an important component. And the entire reaction is just limited by the transport and the movement of ions. And so the specific example that we started looking at was this ion exchange between sodium and lithium, moving it from a rock salt phase to a layered transition metal oxide phase, something that some people might use as electrode material. And so effectively, we've got very similar bonding in both cases, but because you've got the slightly different ion size of lithium versus sodium, you have slightly different lattice parameters of the rock salt phase if you have lithium in there or if you have sodium in there. And so this is something that we can monitor using an in situ diffraction experiment. We can look at the Bragg diffraction peaks, we can pull out the intensities as a function of that reaction progress. And that tells us how far our reaction is going, how fast our reaction is going. So here is some data from that model system that was collected by my student Gabrielle. And what you can see, this is just, she takes the reagent, she puts it in a capillary, the powders in a capillary on the beamline, and she watches that reaction. And we can see the transport kinetics are actually a little bit complex. We see initial fast part, here we go, fast part, and then the reaction slows down. If we take this exact same reaction materials, and we, went too far this time, change something, then we get very different amount of product. So we get much faster kinetics in this case. And we've got instead of getting 20% completion, we're up at 60% completion. Now, the one little change that we made here was instead of just loading our powder in the capillary, like good powder diffractionists would do, we took it and we packed that powder. And that's, instead of getting like 25% of the volume filled with crystallites, we had 85% of the volume filled with crystallites. And so what this means, it is changing what's in the neighborhood of every particle. Every particle then, if we do an analysis, we can see every particle is next to, or almost every particle is next to a neighboring particle that it wants to react with. Whereas we just had that powder loosely packed in the capillary, as we were normally doing our reactions, maybe like 20% of the particles are next to someone that it wants to react with. And so effectively, as we change the architecture of our reaction, we compress our particles, we have a shorter transport pathway and we get more reactivity. We were fortunate to work with Katsuya Thornton's group at the University of Michigan, and they do multi-scale continuum models. So what they were able to do was come up with scenarios where we have the particles next to 2 reactive neighbors, 1 reactive neighbor, and ones that were only collected indirectly via other particles. And they can simulate what that reaction in each of those particles will look like, what that composition will look like over time. And then we can take that reaction progress and we can take the number of nearest neighbors and we can just maths out what that's going to give us. And it gives us something almost exactly like what we're seeing experimentally. So the difference that we're seeing here is just due to the number of neighbors that it can react with, of those particles. And so this tells us something really important. If we want to make our reactions go to completion at lower temperatures, then we want to think about those transport pathways. We want to arrange our microstructure so we have particles in close contact with other particles that they can react with. And this is a bigger effect than increasing the temperature. So we can get much more complete by thinking about that architecture in a special way. So this is obviously very important, but one of the things that I think is most interesting about these data is, like, even though we talked about solid state reactions being slow, actually in the first minute, which is why we were doing the heating of this reaction and just starting it, we actually see a lot of that reaction is happening, and then it slows down after that. So it says that that solid state reactions are not intrinsically slow, even though we've got transport limits here. There is a component that is fast, faster than we were capturing with these measurements. And it sort of like hints at, if we can identify why it's fast or what makes it eventually slow, then it gives us the possibility to design reactions where we maybe heat it for a minute, stop it, reset whatever that thing is, and then go again. And so maybe in 2 or 3 resets, so 2 or 3 minutes, we could have our complete product instead of waiting for however long it takes that to get to 100% completion. And so this early reaction times, this is experimentally a little bit hard for us to probe. If we want to look at the very fast kinetics in our reaction, that means that we have to initiate that reaction on a timescale that's fast relative to the kinetics. And so when we're talking about heating, a reaction that's initiated by temperature, we have to heat the sample fast. And of course, we're not using these kind of muffle furnaces on our beamline, although I guess you could get some high energy X-rays through that, but we're using something like this flow cell furnace reactor where we have resistively heated coils and we have our sample in that capillary. We can even have like a thermal gradient across our sample to look at lots of different temperatures in parallel. But this entire device, there's some thermal mass associated with it. And so the fastest that we're able to heat this up is sort of, if we just put on that temperature at the maximum temperature, it takes about a minute to heat up. So this is where a lot of our interesting things are happening. And so we set about to design a new reactor that will allow us to heat our sample a lot faster. So here it is. It's what my group called the Raptor reactor. We've got the same resistively heated coils here. We have a thermocouple here for temperature control. And so what we do effectively is we preheat this oven, and then we insert the sample. There we go. And so we move the sample in, and so it then heats up as fast as it possibly can. So it heats up, and we're just heating the thermal mass associated with the sample. And so it gives us maximally fast heating, which gives us a chance to look at some of that fast initial kinetics in these systems. We can benchmark that performance, and we can show that it gets to temperature within about 10 seconds. So this is diffraction thermometry, just looks at some temperature standards, and so we can get anything from 50 degrees to, well, this is 750 degrees, but I'm pretty sure we can get up to about 950 degrees C in 10 seconds in order to initiate a reaction and then watch the early kinetics. So here's a test case reaction we did. This is work that was done by my postdoc Bryce. And he was doing a lot of work on synthesizing lead tungstates. So scheelite phases, these are important as photocatalysts or solid electrolyte type materials. But Bryce is a good solid state chemist. He knows that he takes lead oxide and tungsten oxide, he mixes them together, he puts them in the oven overnight at 750 degrees C, and he'll end up with this scheelite. Lead tungstate is a phase pure product. So lead and tungsten, very nicely, strongly scattering. We can put it in and look at these very fast early kinetics without worrying about signal to noise. So here we have data that was collected at 11 IDB. And so you can see the first 10 seconds, we can see peak shift, thermal expansion's happening. We get to temperature, and we can see new phases come in and some phases go away in this first 5 minutes of this reaction. We can go through and do a Rietveld refinement of these data, fit structural phases to them. And what we can see is, well, in 5 minutes, so Bryce was doing this overnight, before he'd left the building, this reaction would have been all over. He would have already made phase pure scheelite. But what's even more interesting is if we look in this first 30 seconds, we actually saw a new phase that we hadn't seen before with a slightly different composition, but this would be our metastable phase, one of these ones that we are often decomposing to more stable phases. So this is indicative of the type of material that we're trying to look for. This was probably before Bryce has even left the lab. Close the oven door. Before he's left the lab, he's made this and it's disappeared. And so it really speaks to the fact that there are very interesting fast reactions happening, and that if we're not looking at these early stages of the reactions, we're probably missing a lot of these interesting materials that are possible to make, but we just haven't identified the right conditions for. So moving forward, we started to expand the types of materials that we're been looking at using this approach. We're interested in, how do we discover next generation energy storage materials? So this is some work where we're looking at the synthesis of 4,5,12 lithium titanate anode materials. It's good for fast charging. Synthetically, it comes from reaction of TiO2 as anatase with lithium carbonate at above 650 degrees C. So again, we can put it in the Raptor, and we can collect data as a function of reaction time. This is about the first 10 minutes, and then we can fit structural models today to pull out the phase fractions and look at that reaction evolution. So what we have here is it actually goes via an intermediate state. So we have anatase reacts with the carbonate. It goes to a 2,1,3 phase that then reacts further with more titanate to form the 4,5,12. And so we can do now we have all this rich data on the kinetics. We can start to do various kinetic analyses in order to understand how the chemistry and what different phenomena are limiting this reaction progress. So one very sort of straightforward approach that we can use, and it's very commonly applied to look at a lot of different types of kinetics, is using an Avrami type formalism. So Avrami takes your kinetic data, takes a couple of logs, and what it does is the slope of that relates to the dimensionality of the transformation. So if you have a high slope, it tells you it's a high dimension transformation. So it might be 2-dimensional or it might be propagating in 3 dimensions. Whereas if you have something that's a lower slope, that's a lower dimensionality of propagation. And so when we take some of that data that we have on this reaction, and now this is done at 482 degrees C, which seems random, but that's 2/3 of the melting point of the lowest melting solid, lithium carbonate. So that's the temperature that you would go to if you were following Tammann's rule for your synthesis. So we can see when we do the Avrami analysis, we end up with two distinct slopes. So we have one slope at the beginning, and then it shifts to a lower slope. So that's telling us that this reaction propagation, the fast part, is associated with a higher dimensionality, and then we have a change in how the reaction is propagating at a very distinct point, and we end up with a lower dimensionality of that transformation. And we can see that that's actually common across all different temperatures. So we can compare the reaction at a bunch of different temperatures, and in every case we have a transition between a high slope and a low slope region. When we're at higher temperatures, we go to that next step again. It also has two different slopes, so two different dimensionalities for that second transformation. And no matter what temperature you're looking at, it's the same slope. So it's telling us that this is something very intrinsic to this reaction, to this system, that's causing this transformation from the high dimensional to the low dimensional transformation. And so this gives us a clue as we start to look at different systems, how we can maybe change this so we can get enhanced reactivity. So change the dimensionality, change the surface disruption, surface roughness, change the interactions in order to then understand, is this what the origin is of that transformation? And so I think what we've sort of taken away about solid state reactions is that even though they're advertised as slow, and it's really nice to leave your reactions overnight, actually there's a lot of very interesting stuff in this fast kinetic regime, and this is often what we're seeing at the earlier stage of the reaction. It might just be because everything that we've been looked at and everything that I've shown you is something that has an application as some kind of electrolyte or electrode material where you do need to have some kind of ionic conductivity. But even if that's just the case, it's only limited to electrolytes and electronic materials. These types of fast reaction kinetics suggest that there's a lot of stuff to look at. We're just not looking at it fast enough, and it sort of opens a rich landscape that we're starting to explore now using our Raptor reactor. It's also terrible for doing beam time because we have to change samples every 10 minutes, but just between you and me. Okay, so switching gears a little bit. So solid state is one of the major ways that we go about making materials. The other way is solution phase synthesis. So where you dissolve up your reagents in solution. Transport's not a problem. You have solvent to mediate that transport. Everything can move around, everything's very dynamic. But the challenge is that you have all this interplay and balance between interactions between a lot of different species and a lot of different moderately weak interactions. And so then controlling which specific phase that you form becomes very challenging. And it's determined by everything you have in solution. So it's a complex reaction space. So the system that we started to look at is a really classic system for looking at polymorphism, and this is TiO2. Just in the naturally occurring polymorphs, there's 3 different phases of TiO2. We're surrounded by one of them. I'm assuming this is paint on the walls, but we're probably surrounded by rutile in the paint. That's the most stable thermodynamic minimum for bulk particles. It's rutile. But as you go down to the nanoscale, you have the smallest particles are stabilized as anatase, and the intermediate particles are stabilized as brookite. This is the ones that we usually want to make. These are the best photocatalysts. Of course, it's in the Goldilocks intermediate size zone. But of course, the reaction conditions in order to make one or other of these, or favor one or other of these, has to be carefully controlled in order to get one specific polymorph. The standard way that we go about synthesizing TiO2, well, there's lots of ways, and there are thousands, literally thousands of reports where people have done this reaction and report some kind of mixture of TiO2 products, is you take titanium tetrachloride or some other titanium precursor, you mix it with water, you put it in some kind of hydrothermal reactor, and you heat it overnight or for a couple of days. It's the usual recipe. And then you open up and you've got some mystery mix of TiO2. Of course, we have X-rays, and we want to ask ourselves what's happening during these reactions. So stainless steel reactors, high-energy X-ray beam definitely can go through that, but you see a lot of the stainless steel. And if you want to look at the weak, ion interactions, and you have dilute species in solution, Stainless steel, not so great. What we really like to use are these types of glass NMR tubes. So we don't do any NMR spectroscopy in my group, but we go through thousands of NMR tubes because they're such a great X-ray reactor and excellent for doing pair distribution function measurements because it's got a consistent contribution to the background. So we were preparing for our X-ray beam time. Of course, we should always prepare and do our homework ahead of time. And I asked my student Brian, I said, we want to know exactly how long we need to put this in the beam for how long is our reaction going to take. Let's come up with an experimental plan, which is always very dangerous to come up with an experimental plan. So I said, just go, put it in the oven, and then open the door every hour or so would be fine. Just take a photo, and so we can see when the reaction is complete. Brian said, that sounds like a lot of work. I'm not into that. And so what he did instead was he took a webcam and he pointed it at the oven door. So he's like peering inside the oven as the reaction goes. And he took an image every, I think it's 10 seconds. And so here we have this hydrolysis reaction, 3 different concentrations here. And well, you can see exactly what's happening. You can see it gets white as you form TiO2, and you can see that TiO2 settle out. And you can get all the kinetics, or a lot of kinetics, just from those images. We can take out and focus on just this middle one for a second, and we can take that out and just sort of like put side by side what all those frames look like. So here we have, you can see, it gets whiter, we're forming TiO2, we can see it settle out, and here's something unexpected. We see it get whiter again, and we see another lot of TiO2 settled out. So we see 2 distinct cycles of TiO2 formation and sedimentation. Of course, we had no idea that that was actually happening in those hydrothermal reactors before we opened them up. And of course, we have these images, and images are just another form of data, and each pixel has certain RGB values. So we can actually take those RGB values, we can transform it to say something like luminance, so that's just how bright it is, and so then we can plot luminance of those pixels throughout the reaction. So we can see we're forming TiO2, we're increasing concentration, and then as it's decreasing concentration, we can see those pixels get less bright. And so it's quantifying what we can intuitively see is the formation of TiO2 and the sedimentation. We can go through and do this at different points because we can see the entire reaction here. And we can see if we take it at different heights, we see different peaks in when we have the maximum amount of TiO2 and when it starts to go down. This is of course not because the reaction is doing something different at different heights within the tube. What this is gravity. So as we have solids settle down, the stuff from above sinks into the underlying solution, and so instead of that going down, it goes up. It continues to go up until that full sedimentation front passes that point. And so, naively, when I was going to do the X-ray experiment, I would have stuck the X-ray beam nicely in the center of that reactor. I would have been seeing something that was totally meaningless, that was the convolution of what happened to the reaction and whatever happened to be sinking from above. So now we know when we're doing these kind of luminance, and also when we go and do our X-ray measurements, we want to be sticking our X-ray beam or looking at that part just underneath the surface. So that tells us what's forming and what's sinking out, and is not convoluted by anything falling in from above. And so we can now take these reactions and look at all these 3 different concentrations, and we can see in each of these, wow, we see these kind of 2 cycles of formation and sedimentation. And it's slower as you go to lower concentrations, unsurprisingly. And, at the lowest concentration, we're seeing it still settling out sort of at the 24 days. So that's probably more time than you could continuously get allocated at a synchrotron beamline. Some people are lucky, maybe some people get more than that, but yeah. And so we can see longer process. This is totally not because we forgot about this in the oven. And so now we can use this. Now we have this understanding of the kinetics, we can go and look at what's happening in the atomic structure. This is our heated sample changer. We, of course, can look at the accumulated solid by moving our X-ray beam rastering across the bottom. And now that we're smarter, we can put our X-ray beam just underneath the surface to look at what's the nature of the species in solution. And so here we have our PDF data. This is stack plots of our PDFs at the bottom and at the top. And what we can see is we can see the sort of evidence of the cycles of stuff forming and then sinking out. So you can see the intensity changes. And then, of course, we can go through and fit various structural models to our PDF data to look at the phase abundance and how it's changing during the reaction. So we can fit our rutile, brookite, and anatase. Always fun to fit a 3-phase with all of them being nano. But what we can see is that at each point, so this is our first cycle here, this is our second cycle of formation and sedimentation, we can see that the product distribution is different. So not only were we not aware that it was during these 2 cycles, but we weren't aware that, it's different products. And so when we took out those hydrothermal reactors and we said, oh, what did we make here? And, trying to link that to the reaction conditions, what you end up as the mixture at the end is not indicative of what's forming in the reaction at any point in time. It's the mixture. And depending on where you stop it during that second cycle, that's going to change your distribution of which, rutile to anatase to brookite. And so part of the reason we think that there's all these different reports of how to make this particular material is because people are not realizing that there's 2 cycles of formation and sedimentation and not realizing that there are different products in there. Of course, maybe we should have realized this to start off with. We know that the solution conditions are changing. As we're consuming TiO2, we're also producing more chloride into the solution. So the ratio of species in there and the species that might be forming or absorbing on the particle surfaces, that's going to change a lot throughout the reaction. So it's not surprising in some ways that we do see a change in the composition. So we've gone on and tried to change this and played around with putting different ions in there to change. So these are not ions that are involved in the reactions, but these are emblematic of some of the species that we were forming throughout the reaction. And so when we put in different ion compositions, you see vastly different kinetics and sort of heights of products coming out. So this is 20 different reactions that we can compare in parallel. We can see it all at once, which is nice. 20 samples is probably more than I really want to do in situ because it's going to degrade. We're going to compromise our time resolution. But what we can do is we can take advantage of our small beams. We can make our beam small vertically, and then we can raster across our sample and then map our sample after the reaction as a function of depth. Anything that's at the bottom was formed first. Anything that's higher up in the reaction, sedimented later in that reaction. And so that we can just reconstruct, by looking as a function of height, what was happening during a reaction at different points in time. So here we have, well, it's a lot of data, but we can go through and do just a model-independent correlation analysis. This is nice. It shows us, well, 2 very distinct states. It just stands out. There was very distinct products forming in each of those cycles of formation and separation. And we can then go through and refine models against the data, pull out the phase distribution, and start to then make a connection to what really was the ion composition at the point that these phases were being formed. So what we found is that X-rays are great, but having those imaging, the very cheap webcam, pointed out the image, gives us a lot of really nice complementary information. And it's telling us not only about kinetics, but it's telling us about this heterogeneity that, of course, we wouldn't be able to see with our pencil X-ray beam. Okay, so I think I'm going to shortcut to some of my summaries and takeaways. So, the bright sources of high-energy X-rays are absolutely critical to be able to understand and predict and control these synthesis reactions. And so it's a really important part of this work. But it's only one part of facilitating this type of synthesis science research. Having access to sample environments and reactors that can control our materials under realistic conditions in real time is of paramount importance in being able to look at materials under these reacting conditions, and in also being able to access the relevant timescales for the transformations in these systems. Advanced billion-dollar tools like the APS are amazingly transformative in understanding these systems, but combining them with sort of maybe less expensive but complementary tools can also be game-changing. And you can bet that almost every experiment that I do from this point forward is going to have a camera pointed at it as well, because I can. Finally, as we keep doing more of these in-situ measurements, we get more and more data. We don't always know what we've made. And starting to apply some of these AI machine learning and data and analytics is really helpful in trying to sort of extract meaningful scientific insights, especially when we don't know necessarily what we've made. And so finally, hopefully I've shown you that material synthesis is complex. We have coupled changes in chemistry and structure, energetics and transport that span from the atomic scale, the interface level, to the particle level, to the full reaction scale where we have heterogeneity that's evolving. So this is 7 orders of magnitude. That's from me to the moon. So this is our materials discovery moonshot. And so if we can understand these reactions, then ultimately we have hope to be able to take that hypothetical material, design a synthesis, and go into the lab and make it in one shot, hopefully. So with that, I want to thank you all for listening. I want to thank my group. This is a picture of my current group, but of course, shout out to all my friends and colleagues in the structural sciences group. It's been wonderful working with everybody. And thank you to the DOE for the funding through our Genesis Center. And so with that, I'll be happy to take any questions.
Hi there, great talk. Just curious, like with the Raptor sort of furnace and stuff, or where your material synthesis, have you considered also tracking the evolving CO2 gas as well for that kinetics?
Oh, absolutely. That's a really good idea. So it's a little bit harder in the Raptor device because it's got closed on one end, but certainly a lot of these sort of capillary type reactors, you can flow gas through, and you just need to hook up a residual gas analyzer to watch those reactions. So really important information. I don't like to set up the RGA, so I usually wait till I'm at the beamline to get somebody else to set that up for me. But yeah, it's a great idea.
Karina, great talk. I was curious in your hydrothermal reactions if you ever notice anything forming at the meniscus. I feel like a lot of the times when we follow a procedure like this and watch it, we find that things are actually forming like at air and then they fall down.
We did see something like that once, and it was really weird and we couldn't understand it. And then we conveniently forgot about that. But yes, I mean, this thing where we shoot an X-ray beam through it and expect it to be representative, I think that's really naive. And certainly, there's sort of different things happening at interfaces with the air, especially if you have volatile precursors. So yeah, I think there's lots of interesting things like that happening. We don't know how to study that yet, so we forget about it for the moment.
Any other questions? Okay, if not, let's thank our speaker again.